AI, and AI, generative AI. It uses AI to bring AI.
Everyone is talking about AI nowadays. Wherever we see, we find AI. AI phone, AI laptop, AI fridge, and maybe someday AI toothbrush will also come. But let us pause the hype for a minute and understand what exactly is AI. This video is going to be very basic and non-technical so that everyone who is not even from the technical background can understand artificial intelligence. So let us move ahead with the question, what exactly is artificial intelligence? Artificial intelligence is not magic, it's not consciousness, and it's definitely not a human brain inside a computer. Artificial intelligence is a system that learns patterns from data and uses those patterns to make decisions or predictions. Let me simplify this even more. When you were a kid, you learned by seeing examples. Suppose you touched fire once, it burned your hand, so your brain learned the pattern that fire is equal to pain. Next time you see a fire, you avoided touching it. Now, artificial intelligence works in a similar way. We give it data in the form of examples, then artificial intelligence learns the pattern from those examples. That process is known as training of the large language model or LLM. LLM, as of now, we can consider is a box which has learned from millions of data examples. So when we give a new input to LLM, based on its learning and identified patterns, it gives us the appropriate output. For example, we train an AI with thousands of photos of cats and dogs, where each photo is labeled like this is a cat and this is a dog. After seeing enough examples, the artificial intelligence starts recognizing the patterns like ear shape, face structure, or fur texture. Now, after the training is over, your AI model is ready to identify the new data based on its learning. So now, when you show a new photo, it will tell you based on its learning whether it's a cat or a dog. Now, most of the people assume that by doing this, the AI model starts thinking. But in reality, AI models cannot think. It simply arrives at a decision of a new photo being cat or dog based on the patterns it has learned from its training. And it will check the probability of new photo being a cat or dog. So it simply says, based on patterns I have seen before, this photo looks 92% like a dog. Artificial intelligence does not create intelligence on its own. It learns only from whatever data we give it to the model in the training. If we train it on a bad data, it will result in bad AI. And if we train it on the data which is biased, then obviously AI responses will be biased. This is why AI sometimes give wrong answers. But the problem is it gives wrong answers but confidently, which makes it more dangerous. Now, if you see AI starts trending very recently, why did it become so popular recently? What really has changed? If you are thinking that AI is something new, then you are wrong. AI is not new. It is there since 1950s. But it became powerful recently because of three reasons: data, computing power, and cloud. We have created a lot of data in the recent years. Every photo, every like, every scroll, every comment, everything you do on the internet is data. And AI needs data like we need oxygen. Secondly, computers have become super fast. Earlier, training a simple AI model took weeks, but now a good GPU can do the same thing in hours. And the third reason is cloud and big companies' involvement. Google, Amazon, Meta, Microsoft all invested billions into artificial intelligence. And suddenly, AI become accessible to everyone. By seeing AI doing amazing work, another question comes to our mind, which is AI intelligent like humans? Well, the answer is no, not even close. We are not even close to creating an AI like Terminator. If anything, AI still needs human supervision to avoid embarrassing mistakes. In our day-to-day life, we are using AI in one or the other form. Most of us use ChatGPT on daily basis, which is a form of generative AI. Generative AI is something which generates new content based on the patterns it has learned in the training. We will be covering Gen AI in detail in our Gen AI video part. Okay, so I hope with this you have some basic understanding of what an artificial intelligence is. In the next videos in this series, we will go step by step into machine learning, deep learning, neural network, real world use cases. And also, most importantly, we'll learn where AI will fail. Now, we have already learned what artificial intelligence is at a very high level. The main goal of artificial intelligence is to make machines capable of taking complex decisions, the kind of decisions that normally require human intelligence and understanding. Now, the obvious question is, how do we actually make machines intelligent? If we look at ourselves, humans do not become intelligent by following some hard coded rules. We learn from our experiences and also from the experiences of other people around us. Over time, this learning shapes the way we think and help us make better decisions in the future. We apply the same idea to machines. So instead of writing thousands of rules, we expose machine to a large amount of historical examples data. This data represents past situations and their outcomes. The machine then analyzes this data using some specialized algorithms and tries to identify patterns hidden inside it. Once these patterns are learned and a new set of input is provided, then the machine should be able to predict the outcome. That prediction may not be 100% accurate, but will be the most likely outcome. This entire process, where machines are trained using data to learn the pattern, is called machine learning. Now, when we say machine learns from data, the next natural question is what kind of data we are giving to the machines. Now, based on the data type, machine learning is mainly divided into three types. First is supervised learning. In this, the machine learns from labeled data. That means for every input data, we already know the correct output. The data is divided into two sections, feature and label. Feature is the set of input details and label is the correct output for those inputs. For example, for a house price prediction, we will have area of the house, location, age of the building type of data under features, and the actual price as a label. We provide enough examples to the machine so that it can draw a pattern and understand how the price is changing based on its features. In the similar way, we can also train machines to predict if an email is spam or if the transaction is fraud or not. In supervised learning, the machine learns the relationship between input data and the output. So when a new input data comes in the future, the machine uses the same learned patterns to predict the output. So in short, we can say supervised learning is the learning with guidance. In this, we tell the machine what the right answer looks like. The next type of learning is unsupervised learning. In this, things are a little different from supervised learning. Here we only give input data, but not the correct output for that particular input. The machine does not know what it is supposed to predict. Instead, it tries to understand the data on its own. It looks for patterns like similar data points, hidden groupings, or common behavior. For example, consider customer data of an e-commerce application. We have data like age, location, number of purchases, average order value, and browsing behavior under the features section. But we do not have any labels. That means we do not know what kind of customer that is. We do not tell the machine which customer is premium or which is not. We provide enough examples to the machine so that it can analyze the data and group similar customers together based on the common patterns. From these groups, we can later understand different types of customer and their behavior. So in unsupervised learning, the main goal is not prediction, it is discovery. The last type of learning is reinforcement learning. It works in a very different way compared to other type of machine learning. In this approach, the machine learns by trying different actions and observing the result. The machine takes an action in a given situation, and based on the action, it receives a feedback from the environment. If the action is good, the machine gets a reward, but if the action is bad, then it gets a penalty. Over the time, by repeating this process again and again, the machine starts to understand which actions leads to the better outcome. This learning process is very similar to how humans learn new skills. We try something, and if the outcome is reward, then we understand that this is the correct way. And if the outcome results in penalty, then we avoid that in the future iteration. Reinforcement learning is commonly used in areas like game playing system, robotics, and self-driving vehicles. These are the systems where decisions needs to be taken continuously based on the changing conditions. In reinforcement learning, there is no fixed data set with correct answers provided in advance. The learning happens continuously through interaction with the environment and feedback received after every action. Now let us understand reinforcement learning with a very simple example. Consider a self-driving car. That car observes the environment using sensors and cameras which acts as the input. Now based on that input, car makes an action like accelerating, braking or turning. If the action is correct, for example, staying in the lane or avoiding an obstacle, then the car gets a positive reward. And if the action is wrong, for example, hitting an obstacle or crossing the lane, the car will get a penalty. By repeating this process again and again, the system learns which action gives better result in different situations. Over time, car improves its driving decision based on these rewards and penalties. Now let me just summarize what we have discussed in today's session. Now we can say machine learning is simply the process of teaching machines to learn from data instead of hard coding rules. And depending on the type of data and the way feedback is provided, the learning can happen through supervised learning, unsupervised learning, and reinforcement learning. Each of these approaches solve a different kind of problem, and that is why there is no single machine learning technique that fits every use case. In real systems, the challenge is not choosing the most complex algorithm, but understanding the problem clearly and selecting the right type of learning for it. Now that we have understood machine learning and its different types, the next logical question is how exactly machines are able to learn complex patterns from data. So this is where neural networks and deep learning comes into the picture. To understand this, let us first look at how human learns. The human brain is made up of billions of neurons, where each neuron receives signals, processes them, and then passes the signal forward. Based on these connections and signals, we are able to recognize patterns, understand language, identify objects, and make decisions. Neural networks are inspired by this basic idea. Neural network is a machine learning model that is designed to work somewhat like human brain. It is made up of small processing units called neurons, and these neurons are arranged in a number of layers. The first layer is always called input layer, and the last layer is always called output layer. And the layers between the input and output are called hidden layers. Each neuron takes some input, applies a calculation on it, and passes the result to next layer. Every connection between neurons has a weight associated with it. So these weights will decide how important that particular input is. When the data flows through the network, the neuron processes the data step by step, and finally an output is processed. Initially, these weights are random. So in the beginning, the predictions made by the neural network are usually very poor, but this is expected. But the real question here is, how does a neural network learn? The learning happens through the process called training, the one which we have discussed in the previous video. During training, we provide the input data and the correct output to the neural network, and then neural network will make a prediction. Then we compare the prediction with the actual correct output. The difference between the predicted output and the actual output is called error. Now, based on this particular error value, the network will adjust its weights slightly. This adjustment happens in such a way that next prediction becomes a little better. This process is repeated again and again with large amount of data. Over the time, as the weights keep getting adjusted, the neural network starts producing better and better results. And this is how neural network learns pattern from data. Neural networks are nothing new. Then what has changed recently? The answer is deep learning. Deep learning is simply a type of machine learning that uses very large neural networks. When a neural network has many hidden layers, it is called a deep neural network. And training such deep neural network is called deep learning. I hope you are clear about both the concepts of deep learning and neural network. We are going to cover neural network in detail in the upcoming videos. Now, one more important question is, why do we really need deep learning? Wasn't the traditional learning enough for the systems? The traditional machine learning works well when patterns are simple and clearly defined. But in the real world, things are not that simple. Some problems are very complex. For example, if you have to recognize faces in the images or understand the text written in different handwritings, these kind of problems and patterns are not obvious. Deep learning helps here because each layer of neural network learns something different. The first layer maybe learn very basic pattern, the next layer learns more complex patterns, and deeper layers learn very high level concepts. For example, in image recognition, early layers may detect the edges and shapes, middle layers may detect the parts like eyes or wheels of a car, and the deeper layers may detect full objects like faces or cars. This layered learning is what makes deep learning more powerful. For generating the most likely outcome, deep learning needs large amount of data. This is very important to understand because deep neural network have millions of parameters. They require a lot of examples to learn properly. If the data is limited, deep learning usually does not perform well. This is one of the reasons why deep learning became successful only recently, because now we have large data sets, powerful hardwares like GPU, and better training techniques. All of these together made deep learning feasible. Now, let me just summarize what we have discussed in this session. Neural networks are machine learning models inspired by human brains. They learn by adjusting weights based on the errors during training. Deep learning is the use of large neural network with many hidden layers. And deep learning is powerful, but it requires large amount of data and computing resources. And just like machine learning, deep learning is just another tool. It should be used only when the problem actually requires it. Otherwise, it will be an overkill. In the real world system, success does not come with using the most advanced techniques, but from choosing the right approach based on the problem.
Now, before we move ahead with deep learning any further, let us take a step back and try to understand the building blocks of artificial intelligence. Everything on AI that we see has math as a foundation. In this series, we will try to understand linear algebra, probability, statistics, and calculus on a very high level without going much deeper. So, let us start with the absolute foundation of linear algebra for AI and machine learning. Today we will try to understand few terms like scalars, vectors, matrices, and tensors. And then we will see what all operations can be done specifically on vectors in today's session. So let us start with the scalar first. A scalar is the simplest thing possible. It is just a single number. So think of things like temperature, age, learning rate, or loss value. In machine learning, whenever you see a single value representing something, that is scalar. For example, the final accuracy of a model or the error value after a training step, that is scalar. Now, when we move from one number to a list of numbers, then we get a vector. A vector is basically a one dimensional array. Imagine you are describing a person using features like his height, weight, or age. So instead of keeping them separately, you put them together as a list, and that list is a vector. In machine learning, input features are usually vectors. So whenever data is represented as many values together, you are usually looking at a vector. Next comes matrix, which is where machine learning really starts to feel real. A matrix is just a table of numbers having rows and columns. If we say one vector represents one data point, then matrix represent many data points together. For example, if you have, let's say, 1000 users and each user has 5 features, then you can store all the data in one matrix with 1000 rows and 5 columns. In neural networks, weights are also stored as matrices because each layer connects many input to many outputs. So most machine learning datasets and model parameters lives inside matrices. Now when things get even more complex, we started using tensors. A tensor is just a general name for data that has more than two dimensions. A very common example is an image. An image is not just height and width. It also has color channels like red, green, blue. So an image becomes 3D structure with height, width, and channels. And if you take many images together as a batch, then it becomes four-dimensional. Now, deep learning frameworks like TensorFlow and PyTorch work almost entirely with tensors because real world data is rarely that simple, which can be represented with vectors or matrices only. The important thing to understand is that all of these are connected. A scalar is a single value, a vector is a collection of scalars, a matrix is a collection of vectors, and a tensor is a collection of matrices. Deep learning doesn't introduce new logic here, it just works with bigger and more structured data. And this is why shapes and dimensions matter so much. If you know what shape of your data has and how it flows from vectors into matrices and then into tensors, you already understand a big part of how machine learning models work under the hood. Now that we understood what all these concepts are, let us move ahead and see what we can do with them, starting with vectors. In machine learning and deep learning, we don't just store data in vectors, we operate on them all the time. This is why vector operations are extremely important. So let us start with the vector addition and subtraction. Now we know that a vector is a list of values, for example, person's height, weight, and age. Now imagine you want to slightly adjust these values, maybe to normalize data, update weights, or apply some corrections. So when we add or subtract vectors, we are basically adjusting values together step by step. And in machine learning, this happens when model weights are updated during the training. The model makes a mistake, calculates an error, and then slightly adds or subtracts the value from its weight vectors to improve the next prediction. So vector addition and subtractions are like fine-tuning buttons of a model. Next comes scalar multiplication. So this is when you take a vector and multiply it with a single number. In simple words, you are either scaling up or scaling down the entire vector. For example, if you want to reduce the impact of some value or slow down the learning, you might multiply it with a smaller number. In training neural networks, this idea shows up as a learning rate. We don't want huge changes, so we scale the updates carefully. Scalar multiplication helps control how big or small a change should be. Now comes the most important operation of all, the dot product. This is the core of machine learning. The dot product is used when a model makes a prediction. So when input data enters a model, it combines with the weights using dot product. In simple terms, the dot product helps the model answer one key question. How strongly does this input matches with what you are actually looking for? Every time a neural network produces an output, somewhere underneath a dot product is happening. This is why the dot product is not optional. It is the core calculation behind all the predictions. So if you understand this idea, you understand how model thinks. Next we have is magnitude of vector. Magnitude simply tells how big or strong a vector is. You can think of it as overall size or intensity. In machine learning, magnitude is important because very large values can cause instability. And this is why we often try to keep the weights small and controlled. We use various regularization techniques to control vector magnitudes so models don't overreact. We can say magnitude helps in keeping the model stable and well behaved. We do not compare two vectors to be exactly same. We often see if two vectors are pointing in the same direction. That comes under angle between two vectors. This is extremely useful in the real world problems like comparing documents, recommending similar products, and finding similar users or images. Now, even if the values are different but the direction is similar, then the meaning is also similar. Now that we have already seen what are vectors and what operations can be done on those vectors, the next important thing to cover is matrices and the operations we perform on them. So this is the core skill in machine learning because once the data enters a real model, almost everything happens at a matrix level. So let us start with the matrix addition first. Matrix addition is similar to vector addition but just on a larger scale. So when two matrices have the same shape, we can add or subtract them value by value. This is commonly used when updating weights in a model. So during training, the model computes, updates, and add them to the existing weight matrices to improve the performance. Matrix addition is great, but the real star of machine learning is matrix multiplication. So matrix multiplication is what allows model to combine many inputs with many weights at the same time. So instead of calculating output one by one, matrix multiplication lets us process the entire batch of data in one go. So in neural network, every layer takes an input matrix, multiply it with the weight matrix, and produces an output matrix. This whole process is called forward pass. So whenever a model is making predictions, whether it is recognizing images or translating text, there is always matrix multiplication that is happening behind the scene. Now let us see why these operations really matter in machine learning. So when we talk about the forward pass in neural network, we are literally talking about the matrix multiplication. Input data is stored as a matrix, model weights are stored as matrix as well, and the outputs are produced by multiplying them together layer by layer. So every prediction your model makes is the result of chain of matrix multiplications. Now matrix multiplication is very complicated and doing that on a large scale using CPU is very time consuming. And that is why GPUs are so important in deep learning. They are extremely fast at matrix multiplication. It is one of the reasons why AI has become so popular recently because now we have more powerful GPUs and the training of models has become quicker. Next, let us talk about the matrix transpose. The transpose of a matrix is created by flipping rows into columns and columns into rows. At first, this may look like a simple operation, but it plays a very important role. During training, when the model learns from its mistakes, it needs to send the error information backward through the network. This process is called backpropagation and it relies heavily on the transpose operation. Let us understand this with a very simple example without much of mathematical equations fuzz. Imagine we have a simple network where input layer, let's say layer 1 has 3 neurons and output layer, let's say layer 2 has 2 neurons. The connections between them are stored in a weight matrix that is of size 3 into 2. Now in forward propagation, the input data moves through layer 1 as row of 3 values. The input data matrix is of size 1 is to 3 is multiplied with the weight matrix of 3 is to 2. The result is the output for layer 2 which is of size 1 is to 2. Now, when an error signal calculated at layer 2, it has a shape of 1 is to 2 to match the output. And during backpropagation, to send the error back to layer 1, we need to multiply it with the weights. But we need the dimensions to align the matrix multiplication. If we try to multiply the error matrix of size 1 is to 2 by the original weight matrix, which is 3 is to 2, it will not work because this is not how matrix multiplication works. For two matrix multiplication to be eligible, the number of columns of the first matrix must be equal to the number of rows of the second matrix. To make multiplication possible, we can transpose the weight matrix. When we transpose the weight matrix, it becomes 2 is to 3. Now the error matrix, which is 1 is to 2, can be multiplied by the transposed weight matrix, which is 2 is to 3. The result is an error signal for layer 1, which is of shape 1 is to 3, which matches with the number of neurons in the input layer. This backward flowing signal tells each neuron in the previous layer how much it contributed to the overall error, allowing the network to adjust the weight accordingly for a better prediction next time. Now let us see why this really matters in machine learning. So when we talk about backpropagation, which is how the model learns from mistake, transpose operations become essential. The gradient needs to flow back correctly, and transpose help to align the data in right shape so the learning can happen. Now without transpose operation, backpropagation would not work. So whenever learning is happening in the neural network, transpose operations are quietly working in the background to make everything fits together. Now let us understand the identity matrix. An identity matrix is a special matrix that behaves like a number 1 in multiplication. So when you multiply any compatible matrix with the identity matrix, the original matrix remains unchanged. This idea is important conceptually because it helps us understand how transformations work. In many algorithms, identity metrics are used as the starting point or reference point, especially in the optimization and matrix based solutions. In optimization algorithms like Cauchy-Newton method or BFGS, we try to find the lowest point of the curve. To find this perfectly, the computer needs to know the curvature of the function. Calculating that curvature is very expensive. So instead, the algorithm says that I don't know the curvature yet. Let us start by assuming it is perfectly flat and uniform in all the directions. So it sets the initial guess to identity matrix. As the algorithm takes steps, it slowly updates that identity matrix, wrapping it until it matches the actual curvature of the problem. It is like starting a game with level 1 character. You have no specializations or stats yet, but as you play, you transform those base stats into specialized builds. The next operation is inverse of a matrix. The inverse of a matrix is similar to division in normal numbers. If multiplying by a matrix moves or transforms the data in one direction, then multiplying by its inverse moves it back. Let us understand this with a very simple example. Imagine you have a point in 2D space at coordinates 3 and 4. We can represent it as a matrix of 2 is to 1. Now let us say we have a matrix A that doubles the size of everything. Mathematically, it will look like this. Now when we multiply our 2D space coordinate point by A, we get a new location which is 6 and 8. Now to get back where we started, we need the inverse of A. Since A doubles everything, the inverse of A must half everything. Now we multiply our new point, which was 6 and 8, by the inverse to get exactly back to 3 and 4. In the world of math, this works because A multiplied with A inverse results in an identity matrix. Now, not every matrix has an inverse, and that's okay. The important idea here is that when an inverse exists, it allows us to undo the transformation. We have already covered vectors and matrices. Let us move one step further and talk about linear equations. At a very high level, a system of linear equations is just a bunch of equations that needs to be satisfied at the same time. You can think of it like constraints. You have some unknown values and you are trying to find the values that make everything fits together nicely. Imagine you have two simple rules: x plus y is equal to 10 and x minus y is equal to 2. Now each equation is a constraint. Geometrically, each one is a line. So finding the values that make everything fits together is simply finding the exact point where these two lines are crossing. Now if the lines are parallel, the constraints are contradictory. That means there is no solution. And if they are the same lines, then constraints are redundant. That means there are infinite solutions. In machine learning, this idea is often written as ax is equal to b. It means you have some input data, some parameters, and an expected output, and you are trying to find the parameters that makes the output matches with the data. Here A is the matrix containing the coefficients. This defines the shape of your constraints. X, on the other hand, is the vector of variables that you are trying to solve for. And in the end, B is the result that we want to produce from our data. So when we say solving Ax is equal to V, we are simply asking, is there a way to choose the values so that everything makes sense together? Sometimes a solution exists, sometimes it doesn't. If your data is consistent and not conflicting, then a solution exists. On the other hand, if the data is messy or contradictory, then there might be no perfect solution. And sometimes there are many possible solutions, not just one. So linear regression is just solving a system like this. You have input features, you have outputs, and you are trying to find the best set of weights that connects them. Even when we do optimization, the core idea remains the same. We are constantly trying to find the values that best satisfy the set of conditions. Even if the perfect solution doesn't exist, we look for the most likely set of values. Now let us move to something even more fundamental: vector spaces and span. Think of a vector space as a world where vectors live and make sense together. If you take vectors and you can add them, scale them, and still stays with the same world, then you are in a vector space. In machine learning, this world is usually your feature space. Every data point is a vector and all of them live in that same space. Now comes the idea of span. Span simply means all the directions you can reach by combining those vectors. If you have few vectors, their span is the entire region they can cover when you stretch them and add them together. Some vectors bring new directions, some didn't get anything. This is the main idea behind linear independence. If a vector adds a new direction that you couldn't reach before, then it is useful. And if not, then it's basically repeating the information that you already have. This connects directly to the machine learning models. The features that you will be providing defines the space your model can work in. Now let us understand both space and span with a very simple example. Imagine your vector space is the entire housing market in the world. Now every house is defined by two features there: area and number of bedrooms. You can visualize this as a 2D graph where one direction represents the area and the other represents the number of rooms. Now any house that could possibly exist, be it tiny studio or a massive mansion, will live somewhere on that 2D space. Now let us look at your input data, which is your vectors. Suppose you have two pieces of data. The first vector is house with 1000 square feet and two bedrooms, and the second vector is with the house 500 square feet and one bedroom. The span here is the collection of all the different house profiles you can create by combining these two inputs. If you double the first vector, you can describe a 2000 square foot house with four bedrooms. And if you add them together, you are describing a 1500 square feet house with three bedrooms. If we see this specific example, the second vector is just half of the first one. They both point in the same direction. Now, because of this, your span is restricted. Even though you live in a 2D housing market world, your data can only describe houses where there is exactly one bedroom for every 500 square feet. You can't use these vectors to describe, let's say, 1000 square feet apartment with a 5 bedroom, because that point is outside of your span. To fix your span and cover the whole space, you would need new vector that breaks the pattern. For example, a house with 1000 square feet but only one bedroom. That new directions open up the span and allows you to describe more houses in the entire vector space. That being said, if your feature space is too small, the model can't capture the patterns properly, which we have clearly seen in our example. And if the feature space is too large, the model starts to memorize the things instead of learning. This is where the ideas like model capacity, overfitting, and underfitting comes from. So when we talk about vector space and span, we are really talking about what a model is capable of learning and what not. Once this concept is clear, a lot of machine learning concept starts to feel less magical and more logical. Now that's all about the linear equations, vector space, and spans. We are going to learn about eigenvectors and eigenvalues. We will understand what are those and how they are important in machine learning ecosystem. We can think of data as something that lives in a space, and when we apply a transformation to data like scaling, rotating or projecting it, most of the data points move around and maybe change their direction too. But there are some special directions that behave differently. These points don't change their direction at all. They might get stretched or squeezed, but they will not turn. These special directions are called eigenvectors. Let us understand this with a very simple example. Suppose you have a square photo of mountain trek on your phone and you want to make that photo twice as wide. So you start stretching it horizontally. Now if there is a diagonal line in the photo, maybe like a hiking trail going up the mountain, that particular line will not only just get wider but also tilts. It used to be steep, but after the transformation, it may start looking more flatter. This is how most data points in a matrix behave. Now, if we look at the horizontal line present in the photo, when you stretch the photo horizontally, the line gets bigger, but they do not change the direction. A horizontal line stays perfectly horizontal even after transformation. The components similar to that horizontal line, which survive the transformation without changing the direction, are called eigenvectors. Eigenvectors are very important because in a messy world of data, transformations mostly scramble everything. Eigenvectors are the backbone of that data. They are the directions that remain stable no matter how much you stretch or squeeze the information. So if you find the eigenvectors, you have found the fundamental orientation of your data. I hope eigenvector is clear to you. Now let us move to the second part, eigenvalues. So if eigenvector tells us the direction, eigenvalues tells us how important that direction is. Or in simple terms, the eigenvalue is the amount of stretching or compression. If the eigenvalue is larger, that means the eigenvector is of very high importance. And if the eigenvalue is small, then that means eigenvector or the direction doesn't change much and carries less information. Now if we consider our previous example of photo stretching, as we are stretching photo twice as wide, that means we are stretching it horizontally, then the horizontal eigenvalue is 2, and as the height didn't change at all, the vertical eigenvalue is 1. So eigenvectors gives us the direction and eigenvalue tells us how strong those directions are. Now we know what are eigenvectors and eigenvalues. Now we need to understand why these matters in machine learning. The real world data is messy and high dimensional. In simple terms, high dimensional means you are looking at a way too many details at once. Like you are trying to describe a house using its color, the number of nails on the floor, the brand of the toaster, or maybe 1000 other tiny details. So, due to this, you have a mountain of information, but a lot of those features or information are either correlated, redundant, or not really useful. What we really want is to find the main direction where the data actually varies the most. This is exactly what principal component analysis does. PCA looks at the data and look for which direction does the data spread out the most. These directions are the eigenvectors, and how much of that data spread in those directions, that will be captured by eigenvalues. So for describing a house, instead of keeping every single feature, PCA keeps only the most important directions. By doing this, now we are able to represent the overall data direction with a very smaller data set, which was earlier represented by a very large data set. The main goal of PCA is to reduce dimensions while maximizing variance. To achieve this, it can be divided in 5 standard steps. The first one is standardize the data. Now, it is possible that variables in dataset may have different scales. So PCA scales the data so that each feature has a mean of 0 and standard deviation of 1 to prevent the features with larger magnitude for dominating. Let us try to understand with a very simple example. Imagine you are evaluating two people based on their annual salary and age. Now, if you look at these numbers, the difference in the salary is 5000 while the difference in age is only 15. Now, because 5000 is much larger than 15, the algorithm will think that the salary is more important or has more variance. It may completely ignore the age difference because it looks like a tiny rounding error compared to the thousands of difference in dollars. Now to fix this, PCA scales the data so that they are in the same playing field. It transforms the number so that the mean of every category becomes 0 and the standard deviation becomes 1. Now after scaling, our data may look like this. Now a change of age is just as visible to the algorithm as change in salary. PCA can now accurately find the patterns across both variables without being blinded by the big numbers. Now, second step after standardization of data is to compute the covariance matrix. Suppose we have n number of features. Now, n cross n matrix is calculated to identify how variables correlate with each other. If the positive values are there, that means the positive correlation is there, while negative value indicates the inverse correlation. Now, after calculating this, we need to calculate the eigenvectors and eigenvalues to find the direction and importance of that data. In the next step, eigenvalues are sorted in the descending order to rank the principal components from most informative to least informative components. Now, the top k components with highest eigenvalues are selected. That allows us to reduce the dimensions while preserving the maximum variance of the data. Now, in the end, the original dataset is projected onto selected top k eigenvectors to form a new reduced dataset. The result is the new dataset with fewer features that are uncorrelated and organized by significance. So, this is how dimensionality reduction works. In this, we are not throwing away the data randomly. We are keeping the directions that matter the most and ignoring the rest. This makes model faster, simpler, and often more stable. High dimensional data can be hard to understand, but once you project it onto the most important directions, then patterns become visible. Another important intuition here is data variance. Variance simply means how much of the data changes. Eigenvalues are directly connected to the variance. Large eigenvalues means high variance and strong patterns. On the other hand, small eigenvalues means low variance and mostly a noise. So when we talk about eigenvalues and eigenvectors, we are really talking about understanding the structure of the data. So using eigenvalues and eigenvectors, we are trying to learn which direction matter and which don't. Today, we will discuss two concepts that affect almost everything in machine learning, but people don't really talk about them. I'm talking about matrix rank and determinant. So, let us start with matrix rank first. At a very high level, the rank of a matrix tells us how much useful information that matrix actually contains. A matrix is a collection of data stored in rows and columns that we already know. Now imagine some columns are basically saying the same thing in different ways. They may look different, but they don't really add any new information. In that case, even though the matrix may look big to you, but the amount of useful information inside that matrix is very small. And that is exactly what metric rank capture. Rank tells us how many truly independent pieces of information are present. So when the rank is high, it means data has rich, varied information. And when the rank is low, it means there is redundant data. In machine learning, this happens when two or more features carry almost the same information. For example, if you have both height in centimeter and height in meters, then one of them is unnecessary. They don't add any new insight, they just repeat the information. Now remember the example that we have seen while discussing vector space and span. There we had two vectors. One was representing data for house 1000 square feet area and two bedroom, and second one was 500 square feet area and one bedroom. Now if we see both the vectors have same direction, that is, if we double the second vector, we will get the first vector. So having second vector does not add any extra information. Low rank is often a signal of a kind of redundancy. If we have mostly redundant features, that can confuse the model and slow them down. And this will also make the model unstable. Model stability simply means how sensitive a model is to small changes in data. So if small change in input cause a huge change in output, then the model is unstable. Low rank or redundant data often lead to this particular problem. So rank gives us a way to reason about the data quality and feature usefulness. Now let us understand the determinant as well. The determinant is one of those terms that sound very mathematical, but the meaning is very simple. So at a very high level, the determinant tells us two things. First is if the matrix is invertible or not. Invertible means whether we can reverse a particular transformation or not. So if a transformation squashes space in such a way that the information is completely lost, then you can't reverse it. A zero determinant usually means the information was lost and reversal is not possible. The second thing determinant tells us is matrix scale space. You can think of it as a volume scaling. If the determinant is large, then the transformation expands the space. And if it is small, then the transformation compresses the space. And if it is zero, the space collapses in some direction, that is data loss. Now let us understand why does this matter in machine learning. Now, because model rely heavily on transformations, and if transformation collapse information or amplify noise, then the model becomes unstable. So determinant gives us the indication about our data transformation, whether they are safe or meaningful. If something suddenly becomes non-invertible, mostly it means the data has some serious issues. So rank and determinant together helps us understand the data quality. I hope both the concepts are clear now. Now let us move to something extremely practical and used everywhere, which is norms and distance measures. A norm is simply a way to measure size of a vector, or we can say distance between 2 points in the data space. We have different norms, and different norms measure this size or distance in different ways. Let us start with L1 norms. The L1 norm is also called Manhattan distance. So here think of moving inside a city with a grid like roads. You can't move diagonally, but you have to go street by street. So you add up how much you have moved in one particular direction. That is exactly what L1 norm does. It measures distance by adding absolute differences. So due to this, L1 norms are there for simplicity. And in machine learning, when we use L1 based regularizations, it pushes some value to become exactly zero. Regularization is a technique used to prevent models from becoming too complex. Complex models tend to memorize data instead of learning the pattern. Regularization adds a small penalty for large values, forcing the model to stay simple. L1 regularizations does this by removing less important features. That is why it is great for feature selection. Now let us move to L2 norms. It is a straight line distance between 2 points, unlike L1 norms. So this is what we usually think as a distance in everyday life. L2 norm measures how far things are in smooth continuous way. In machine learning, L2 regularization doesn't remove the feature completely. Instead, it keeps all the features but control their magnitude. Magnitude simply means how big the values are overall. Large magnitudes can make the model unstable and overly sensitive. L2 regularizations keep values small and balanced. This leads to smoother models that generalize better. Now let us talk about Frobenius norm. This is the one norm which is used for matrices instead of vectors. We can think of it as an extending the idea of L2 norm to a whole matrix. So instead of measuring the size of single vector, you measure the overall size of all the values inside a matrix. This is useful when we want to control the size of weight matrices in neural networks. Now, why do norms and distances matter so much? It is because they show up everywhere. For example, in loss function, they uses the distances to measure how wrong a model's prediction is. Clustering algorithm also uses distance to group the similar data points together. Even optimization depend on norms to decide how big or small an update should be. So norms are not just mathematical tools. They define how the model sees similarity, error, and stability. So once you understand these indications, a lot of machine learning behavior suddenly starts to make sense. Now in linear algebra for AI, we are left with only one main topic, which is linear transformations. Now let us talk about linear transformations. And this is one of those topics where it really helps to think visually instead of mathematically. If you already know how neural network work, even on a very high level, then you will be amazed to see how linear transformation help in that. Until now, we have been saying matrices store numbers and perform multiplications. But there is another very powerful way to look at a matrix. A matrix is not just a container of values. It is actually a machine that transforms data from one form into another form. Now imagine you have a set of points drawn on a graph, and if you multiply those points with a matrix, the points may rotate, stretch, shrink, or even tilt. Nothing magical happens here. The data is the same, but the representation changes. This idea of changing representation is what we call linear transformation. Now, this is exactly what happens inside a neural network layer. When data enters a neural network, each layer takes input numbers and transform them into a new set of numbers by multiplying the input with the weight matrix and adding the bias value. It is not simply storing or passing the value, it is reshaping the data's meaning itself. For example, suppose you are building a model that recognizes handwritten digits. The raw input is just a pixel value, which is a grid of numbers that on their own don't mean much. The first layer of neural network might transform these pixels into simple patterns like edges and lines. The next layer might transform those edges into curves and shapes. The deeper layer might transform those shapes into something meaningful, like this looks like a number 3 or this looks like a number 8. Now, here each layer basically is saying, let me look at this data from a slightly different angle. That different angle itself is a transformation. Another simple real world example is facial recognition. An image is just a collection of raw pixels. So, after the first few layers, the network is no longer thinking in pixels. It is thinking in terms of eyes, nose, and mouth shapes. Further layers think in terms of full faces. So the data is not changing physically, but the interpretation is evolving layer by layer. This evolution is nothing but the repeated linear transformations followed by small non-linear tweaks. So this is why we say neural network layers are transformations where each layer is like a filter that changes how the data is viewed and turning that raw number into a meaningful feature. Now, there is another important term which is change of basis. Change of basis simply means describing the same thing or the same data but using different reference system. Think of it like describing distance in kilometers versus miles. The object is the same, only the viewpoint changes. In machine learning, this is similar to moving from raw data into feature space that is easier for the model to understand. This directly connects us to the feature extraction. So feature extraction is nothing more than transforming the raw input into useful signals. For example, in a music recommendation system, the raw data might be sound waves. So after transformations, the model starts seeing tempo, pitch, rhythm, and genre patterns. In text analysis, raw letters become words and words become meanings and meanings become intent. So when we talk about linear transformations in artificial intelligence, we are really talking about the model's ability to look at the same data in different ways. The key intuition here is that machine learning is not only about numbers, it is about changing perspective on numbers until the pattern becomes obvious. Matrices and transformations are simply the tools that allow neural network to perform this change of perspective again and again, layer by layer, until a useful information emerges. Now, with this, I hope you have the required basic understanding of linear transformation and the importance of it in overall artificial intelligence system.
Now we have covered most of the algebra required for artificial intelligence and machine learning. Before we jump into statistics or calculus, there is one very important idea we need to understand, that is probability. So suppose we give a photo of a cat to an AI system and ask it to identify it. Artificial intelligence systems will rarely be 100% certain about something. It will always be like, I'm 80% confident that this provided photo is a cat. So probability is basically the chance of something happening. If I toss a coin, I don't know for sure whether it will be heads or tails, but I know both are possible, right? In artificial intelligence, instead of coins, we deal with things like, is this email spam or is this image of a dog or a cat? And the model answer in terms of likelihood. Now let us try to understand this with events and outcome. An event is something that can happen, and outcomes are the possible results. For example, in rolling a dice, the event is rolling a dice, and the outcomes are, the numbers 1 to 6. In machine learning, the event might be giving an input image to a model, and the outcomes might be labels like cat, dog, car, or a tree. The model doesn't know the answer, it just kinds of estimate which outcome is more likely. So this is where the idea of random variable also comes in. A random variable is just a way of saying that it is a value that can change depending on the situation. For example, the number of people visiting a website tomorrow is not fixed. It can vary actually. In artificial intelligence system, many inputs behave like this, like user behavior, clicks, time spent. All of these are not fixed numbers. So models are constantly dealing with changing values rather than any constant. Another important term in probability is distribution. Now, when we talk about probability distribution, we are simply talking about patterns in data. For example, most students in a class might score around, let's say, 70 to 80 marks, and there will be fewer students who scored 95 and above, and very few will score lower than 30. So, there is a visible pattern there. In artificial intelligence, understanding these patterns help model know what is normal and what is unusual. Fraud detection systems work heavily on this particular idea. They look for transactions that fall outside the normal pattern. Another important concept here is mean. Mean you can think of as average or the expected value. If you repeatedly measure something, the mean tells you the kind of center point where things usually settle. So, closely related to this is variance and standard deviation, which simply tells us how spread out data is. For example, students in two classes in a school can have same average marks, but in one class it is possible that everyone scored close to the average, while in the other class scores might be all over the place. So that spread actually matters a lot in machine learning because it tells us whether the data is stable or unpredictable. Another important concept is conditional probability, which is basically saying if this has already happened, what are the chances of something else happening now? For example, if someone is searching for laptops, then the probability that they might be searching for accessories will increase. Recommendation systems and advertisements works heavily on this particular idea. They are not guessing randomly, they are actually adjusting probabilities based on what already has happened. Now the big question is, why does all this matter in machine learning? Answer is simple, because almost every prediction a model makes is actually a probability. Even when your phone unlocks using face recognition, it is not absolutely certain. It is just highly confident. So when Netflix recommends a movie, it is saying based on your past behavior, there is a high chance that you would like this particular content. Even simple spam filter don't say this email is spam for sure. They say something like there is 95% probability that this is a spam. All these systems work on something called confidence score. So for example, if we give a picture of a cat to a classifier, the output it will generate will be numbers like zero point 0.9 for cat, 0.08 for dog, 0.02 for other. Those numbers are nothing but probability. The classifier is telling that the pattern is matching 90% with cat, 8% with a dog, and 2% with something else. Let me actually tell you a real story of how this works in practice. A few years ago, Google Photos had an embarrassing incident where their AI mistakenly tagged some people as gorillas. Now, here is what was actually happening behind the scene. So, when you upload a photo, the model doesn't just say gorilla or not gorilla, it calculates the probability of thousands of categories simultaneously. So, it might output something like human face 0.65, gorilla 0.28, and other primate 0.05. Now, ideally, human face should have been way higher, like 0.95 and above. But in those problematic cases, the model was giving similar probabilities in both the categories, maybe 0.48 for human and 0.52 for gorilla. So when the probabilities are that close, the model is basically confused. It is not confident at all. Now, to fix this issue, Google didn't just remove the gorilla label. They had to retrain their entire model to create a bigger gap between these probabilities. That gap in probabilities is what gives us confidence. And this is exactly why we need something called confidence threshold in production systems. Most companies won't even show you a prediction if the highest probability is below, let's say, 80%. Because if the model isn't sure, why should we trust it, right? The label with the highest probability becomes the prediction, but the probability themselves tells us how sure the model actually feels. So probability in artificial intelligence is not about gambling or dice games. It is about giving machines the ability to say that I'm not absolutely sure, but based on what I have seen before in my training data, this is the most likely answer. Now, probability gives us the foundation to understand uncertainty, but there is actually more to the story. In the next session, we are going to dive into statistics for artificial intelligence and machine learning. And this is where things get really interesting because statistics is how we actually make sense of that data. It is everyone's dream to work in a FANG company. Suppose you have done everything like prepared for DSA system design before you apply. And when you apply, the AI system in place to filter resume rejected you, not because of your skills, but because of your gender. Back in 2016, Amazon built an AI hiring tool to filter resume automatically. They trained that AI on 10 plus years of hiring data and expected it to find the best candidate for them. But within 2 years, they had to completely shut it down because the model was systematically rejecting women candidates. Now, it was not because someone programmed it to do that. But because the data it was trained on was mostly male dominated and nobody stopped to actually understand what that data was actually saying. The algorithm wasn't broken here, the data understanding was. So before you touch a single line of code, let us talk about what your data is actually telling you. So, what kind of data are we actually giving to artificial intelligence systems? For a model to predict anything, it has to first look at the data. And unfortunately, real world data is never clean or organized, which we can use straight away. And this is where statistics comes in. Statistics is not about complex equations. It is actually about understanding how the data behaves. So let us start with the most basic concepts first, population and sample. Population is the entire set of data taken as a whole, but a sample is a small portion taken from that population to understand the pattern. For example, if you want to understand the behavior of all the users on a platform, then all user data is a population, but in reality, you will never have data for everyone, right? So you take a sample, you select a few users from all the users. So in machine learning, we always work with samples, not the full population. Whatever patterns we learn from the sample, we assume they represent the entire data set. Now, here is where it gets dangerous. If your sample is not representative, like Amazon's hiring data was mostly male, your model learns the wrong thing with full confidence. That is where the bias enters the system. Now, once we have the sample data, the next we have to find the center of this data. So this is where mean, median, and mode comes in. Mean is the average calculated by dividing sum of the values by count of the values. Suppose we have salary data of 5 employees and let us say they are earning 10, 20, 30, 40,000, and one person is earning let's say 100,000 per month. So in this case, the mean will be sum of all these salaries divided by 5. That comes out to be 40,000. So here mean gives the expected value the model will try to learn for predicting a new outcome. But as you can see here, most data points are below 40. So the mean represents the value that most data does not actually support. Models that rely heavily only on mean can be misled by extreme values like it happens in this case. Now imagine you are building a salary prediction model and you use mean as your reference point. Your model will consistently overestimate what most people actually earn. So that is a real problem. So this is exactly why median exists. Median is the middle value when data is sorted. So when we have a sample data and we sort it in any order, then what value comes in the middle is called median. So for the same salary data, when we sort it in ascending order, the median comes out to be 30. So this is more accurately representing what a typical employee at that particular company earns. It is more stable than mean and it is mostly used when we want resistance against the extreme values like we have 100,000 here. Here we can see the mean was affected by the outlier value 100,000 and compared to it the median is more stable and representative of the entire dataset. Now many real world dataset behave closer to median than mean. The next concept is mode. It represents the most frequent values. Now suppose we have a data with the values 10, 20, 20, 30 and 40. So in this case the mode will be 20. In classification problems, the most common class can dominate the model behavior. So if not handled carefully, model may learn to produce the output towards mode values more often and ignore the minority patterns. Going back to Amazon, if most hired candidates in the training data were male, then male essentially became the mode of successful hires. The model learns to favor male as expected outcome due to this particular pattern only. Now, all these mean, median, and mode are the ways to find centers of data. But why do we need three different centers? If we see real world data, it is not always balanced. For example, a few extremely high values can actually pull the mean upward. In such cases, median gives us the better idea of what is typical. In machine learning, choosing the wrong center can misrepresent the data, which will result in wrong outcomes. Now, knowing only the center of data is also not enough. We also need to understand how spread out the data is. To understand that, we have variance and standard deviation. Let us think of two classrooms with the same average marks, just like in our previous probability video example. So, in one class, almost every student is scored close to the average, but in the other class, some students scores very high and some are very low. So that resulted in the same average but completely different behavior. In machine learning, data with high spread is harder to predict because it is difficult to identify a pattern in that data. But the data with low spread is more stable because there we know the pattern will form and output can be predicted with more confidence score. If Amazon had measured the spread of gender distribution in their training data early on, they might have caught the imbalance before it corrupted the entire model. The next concept is data distribution. Basically, it answers what shape does your data form when you plot it on a data space. Some data forms a bell curve where most values lies in the middle and fewer at the extreme sides. Some data is skewed where most values are on the one side with a long tail on the other side. Like this, there can be different distributions of data. Models learn differently depending on these shapes, and if you don't understand the distribution, the model can behave in surprising ways. Now, you might be thinking with all these concepts, it will be very easy for a model to identify the patterns, right? Now, here is the reality check. Real world data is a mess. It has missing values, noise, errors, and I hope you remember the Amazon AI is rejecting women due to biased data. So we can say that data is rarely clean and perfectly distributed. Amazon's mistake wasn't a modeling mistake, it was a data understanding mistake. They didn't ask what patterns are hiding in this data before training. So instead of blindly feeding the data into models, statistics helps us find these imperfections. So the purpose of statistics in artificial intelligence is not to impress anyone with formulas. It is to help us answer one simple question: what kind of data am I dealing with? Because if you understand your data, then half of machine learning problems are already solved. And if you don't, then even the best models will struggle. Now, we will take this understanding one step further and see how data behavior directly affects the model behavior, including things like overfitting, underfitting, bias, and evaluation metrics.
A few years back, we started using AI in judicial system, and then it starts flagging all the black people as criminal. It was the year 2016 when US courts decided to use AI system for deciding who goes to jail and who goes free. That AI system was called Compass. Its main job was to predict whether a current criminal would do something bad again in the near future. That sounds amazing, right? Stopping the crime before it even happened. The model behind the AI system was having decent accuracy on, but most of the time that AI system was flagging black person as future criminal compared to the white person. This was a classic case of overfitting. Today we are going to understand exactly how that happens and more importantly how statistics can help us catch it before it becomes a real world problem. Now, previously, we have focused on understanding the data itself. We talked about center, spread, and distribution. Now, let us understand what happens when a model starts learning from that data. Models don't just consume data, they react to that data. Statistics plays a very important role shaping the model behavior. So, we will cover all the important concepts which are required to understand the behavior of the model based on that. So, let us start with the first concept. The first concept is bias. Bias is actually a very tricky word because it means different things in different contexts. Now imagine you are trying to hit a target with arrows, and if all the arrows hit far from the center but they are all grouped together in one spot, that is bias. It means you are consistently missing in the same direction. In machine learning terms, bias is when a model makes systematic error. It is not making random mistakes. It is the same kind of mistakes every single time. It is possible that the model has learned something incorrectly, or maybe it is too simple to capture the real pattern from data. This is a straightforward case of model underfitting. Underfitting occurs when a machine learning model is too simple to capture the structure of the data. That results in low accuracy and high error rate on both training and validation data. Now you need to understand one thing here: you cannot completely remove bias because we are always working with samples and not the full population. So bias will always be there. On top of that, we are always using simplified mathematical models to represent the complex real world problem. The goal here is not to eliminate bias completely, but to keep it low enough so that the model is still used. Now think about Compass here, the same AI tool used in judicial system. The model had a systematic direction of error because it consistently flagged one group more than the other. That is exactly what high bias looks like. Now bias is one thing, But there is another side of the story, which is variance. Variance is kind of opposite to bias. Going back to our arrows example, if your arrows are scattered all over the place, some are near the center, some are far away, but with no consistent pattern. That is the significance of high variance. In machine learning, high variance means the model is too sensitive to the training data. Due to this, it starts picking up noise and random fluctuations instead of the real pattern. So if you show the model slightly different training data, it makes completely different prediction. This is known as overfitting. Here, model starts memorizing the training data instead of learning the general pattern. Overfitting occurs when a machine learning model learns training data too well and it starts memorizing irrelevant patterns rather than generalizing. That results in high accuracy on the training data but poor performance on the new data. Now think of a student who memorized every single example from the textbook, but when presented with a new problem which is not there in the textbook, he is unable to solve it. This is the classic example of overfit. So with bias and variance, now we have two problems at hand. One is when the bias is high, that means the model is too simple and that causes underfitting. And second one is when the variance is very high. That means the model is too complex and that causes overfitting. But we cannot remove bias or variance completely. There is always a trade-off between them that we need to consider, which is also known as bias variance trade-off. If you make your model more complex to reduce the bias, the variance will go up. And if you make it simpler to reduce the variance, then the bias will go up. So we need to find a sweet spot, which is a balanced point for both bias and variance. Our end goal should be for a model that is complex enough to capture the real patterns, but simple enough that it doesn't memorize the noise. Now, to handle and validate this balance, we usually split the data into two parts, training and testing. We train the model on one part and then test it on the data it has never seen before. If the model performs well on the training data but poorly on the test data, that's a clear sign of high variance or overfitting. And if it performs poorly on both, that is usually means high bias or underfit. The model behind Compass AI system had a different problem. It performed consistently but consistently wrong for one group. That is the danger of bias hiding behind the high accuracy on. So now I hope the concepts of bias, variance, overfitting and underfitting are clear to you. If not, please do let me know in the comment section. I will try to explain it more if required. Now let's talk about two more concepts that mostly confuse people: correlation and causation. These two words may sound similar, but they represent different things, and confusing them with each other will lead to really bad decision in machine learning. Let me start with correlation first. Correlation simply means two things tends to happen together. So when one goes up, the other also goes up or down. There will be a clear pattern or relationship between both the. For example, electricity consumption and ice cream sales both increase in summers. That means they both are correlated. Because if you plot them on a graph, you will see both rising at the same time. But the important thing to understand here is correlation does not mean one is causing the other. Because if you see, using more electricity does not make people buy more ice cream. They both just happen to increase because of a third factor, which is hot weather. This is where causation comes in. Causation means one thing actually causes the another thing to happen. For example, if you water a plant, it grows. So we can establish that watering the plant causes growth. That is causation. If two events are correlated, that does not mean one is causing the other. And this is a huge problem in data analysis and machine learning. Because machine learning models are really good at finding correlation. They can spot patterns in data very easily, but they have no idea about cause. A model doesn't understand why something happens. It just sees what happens together. Now let us understand this with an example. Suppose a model notices that people who buy expensive shoes also tend to have higher credit score. Here we have two variables. One is buying expensive shoes and the other one is credit scores. We can say these two variables are correlated. But does buying expensive shoes causes high credit scores? Well, obviously not. It's more likely that people with higher income can afford expensive shoes and they also tend to manage the credit. So if you build a recommendation system that says buy expensive shoes to improve your credit score, that is just completely wrong. The model here saw a correlation and assumed the causation. Now let us connect this back to the Compass AI system. The model likely found correlation between certain historical records and reoffending rate. But those correlations were the result of deeper systematic inequality, not the causation. So in machine learning, we have to be very careful. Models will find correlation all the time. But whether those correlations actually mean something useful and one thing is causing the another, that requires human judgment. We can't just blindly trust patterns in data. This is why domain knowledge is so important while working with artificial intelligence. You need to understand the problem, not just the data. That can be done by asking simple question. Does this correlation make sense or it is just a coincidence? Because sometimes correlations are real and useful and sometimes they are just noise or a result of some hidden fact. Okay, so I hope now you are clear with what is correlation and causation. If not, do let me know in the comment section. Now, once the model is trained, the next obvious question is how do we know if the model is good or not? That is where evaluation matrix comes in. And this is also where the compass story gets most interesting because on paper, the model was looking very good. The accuracy was acceptable, but accuracy alone was hiding something critical. So let us understand why. Starting with the simplest metric, which is accuracy. Accuracy tells us how many predictions the model got right overall. But accuracy alone can be very misleading. For example, if we have a model that always predicts an email as not spam, and if let us say 99% of the emails are not spam, then that model will have 99% accuracy. But alone accuracy is completely useless. It is useful in combination with precision and recall metric. Now, precision tells us out of everything the model predicted as positive, how many were actually correct. Imagine your spam filter flag 100 emails as spam, and out of those 100, only 40 are actually spam. The other 60 were normal, important emails that got wrongly flagged. That means the precision of your model is 40%. Even though the model is catching spam, it is also ruining your inbox by trashing the important emails as well. Recall, on the other hand, tells us out of all actual positives, how many the model manages to catch. Now imagine there are 100 patients actually have cancer and your model only manages to detect 30 out of them. The other 70 get a healthy result and go home untreated. That means your recall is 30%. The model looks fine on paper, maybe even has decent accuracy, but it is missing the majority of real cases. These two metrics often pull in opposite direction. So if you make your model super aggressive, flagging everything as spam or detecting everyone as a cancer, then your recall goes up but your precision goes down. And if you make it very conservative, the precision goes up but recall drops. That is why we need to maintain a balance between these two depending on what problem the model is solving. Now, I hope you understand the problem. Precision and recall are both important, but they pull in opposite direction. That means if you try to improve one, the other will suffer. So how do we get a single number that balances both? This is where F1 score comes. F1 score is a combined measure of both precision and recall. Technically, it is the harmonic mean of these, which means it is not a simple average but a balance between them. This is how F1 score is calculated. 2 times the multiplication of both precision and recall and then divide by their sum. The reason harmonic mean is used instead of simple average is very important. If precision is 90% and recall is 10%, a simple average will give you 50%, which is very decent. But F1 score will give you around 18%, which correctly tells you that the model is actually very bad. F1 score is especially useful when your data is imbalanced, like our spam example, where 99% of the emails were not. In those cases, accuracy is useless, and even precision and recall alone can be misleading. So, F1 gives us the honest picture. Now, we have covered a lot of essential concepts in today's session. It is time to discuss a couple of important questions as well. The first one is we usually hear that more data means better model, which is not true, but up to some extent it is true. Now let us understand why. Now think about how humans learn. If you want to teach a child how to recognize dogs, and you show them only 3 pictures of small brown dogs, they might think all dogs are small and brown. But if you show them 1,000 pictures covering all the breeds, sizes, and colors, they build a much stronger and more accurate understanding. Models work in the exact same way. So when a model is trained on a very little data, it only sees a narrow slice of the real world. With more data, it learns what is noise and what is normal. With a small data set, the model cannot tell the difference between a real pattern and a noise. It might actually memorize the noise thinking that it is important. But when you have a large data set, the real patterns show up consistently across thousands of examples. So the model naturally learns to trust the patterns and ignore the noise. It also helps in reducing the overfitting problem. But here is a catch. More data helps only when the data is good. And this is the part most people overlook. Now imagine you are trying to teach someone how to cook, but all your recipe books have wrong measurements and missing steps. Now reading 1000 bad recipes won't make them a better cook. It will just make them confidently wrong. Compass had plenty of data, years and years of criminal justice record. But that data carried a decades of systematic bias baked into it. More data didn't make it fairer, it made it more confident in its unfairness. Now, this brings us to the final question. Data quality versus model complexity. You can have the most advanced model in the world, but if the data is noisy, biased, or wrong, the output will always be wrong. On the other hand, simple models trained on a high quality data mostly performs well. In the real projects, improving data quality gives better results than making the models more complex. Be it Amazon's hiring AI, Compass, or other countless real world failures, they all had one thing in common. Not the bad algorithm, but the bad data understanding. The algorithm wasn't a problem. What was feeding the algorithm, that was the main problem. With this, I conclude the statistics topic in our AI series. With all these discussions, we can say that the statistics helps us understand not only data but also the model behavior. We also saw how data quality has more impact on the output than the complexity of the model. And the next time someone shows you that their AI system has 95% accuracy, you will know the right questions to ask, like what is the precision and recall? And what does the training data actually look like, because now you understand what those numbers are really saying. So with this we conclude the statistics which is required for artificial intelligence and machine learning. In the next video we will cover various optimizations in machine learning before we start with calculus. But if I tell you that you don't need to build any complex model to improve the prediction accuracy and quality, you just need to see how you can minimize the errors. And that is exactly what happened with Netflix. Back in 2010, Netflix organized a competition where they had put $1 million prize for anyone who could improve their recommendation algorithm by just 10%. Then thousands of teams from around the world participated in this competition, and the winning team did something extraordinary. They didn't find any better data or build more complex model. They just got really good at one thing, which was minimizing errors. They kept adjusting and improving step by step until the model was as accurate as possible. That process of constantly reducing error and finding the best possible version of the model is called optimization. And today, that is exactly what we are going to understand. Because optimization is the engine behind every AI system that you have ever used. Whether it is Netflix recommending you next show or ChatGPT generating responses, optimization is running in the background of all of these. So let us understand exactly how it works. Previously, we have covered statistics. Now we understood data, model behavior, bias, variance, and evaluation metrics. But there was one question we never answered. How does a model actually get better over the time? Like when you train a model, what is actually happening inside? How does it go from making a terrible prediction to actually useful ones? That is what optimization answers. So let us start with the first question. What does optimization actually mean in machine learning? Optimization means reducing the mistakes a model is making as much as possible. When model makes a prediction, it will be wrong sometimes. Optimization is the process of figuring out how wrong it is and then fixing it. This loop continues for a very long time again and again until the model stops being wrong. Think of it like this. Imagine you are trying to park a car in a very tight spot. In your first attempt, you may be too far from the left side. So you move back and try to adjust. Now, in the second attempt, you might be fine from the left side, but maybe slightly too far from the right side. So you adjust again. You keep making these small corrections until the car is parked properly in the spot. That back and forth process of adjusting and correcting is optimization. In machine learning, you can say the model is the car and parking a spot is the correct answer. So optimization is everything that happens in between. Now, for optimization to work, the model needs to know how wrong it is. And this is where loss function comes in. The loss function is simply a way to measure the model's mistake. It takes model's prediction and compares it to the correct answers. And then it gives back a number. The higher that number means model is more wrong, and lower number means model is closer to being right. So the entire goal of training a model is to make this number as small as possible. Sometimes it is also called cost function, which means how much the model currently getting wrong. and everything the model does during training will be towards making this number as small as possible. Now, can you visualize a landscape like a hilly area with mountains and valleys? Every point on that landscape represents a different version of the model with different settings and parameters. The height of any point on that landscape represents the loss, which means how wrong the model is at that particular point. So we can say that peaks and hills are where the model is very wrong. And the valleys, which are the low points, are where model is doing well because the loss value is small. This entire landscape we can call as error surface. And the only job of optimization is to find the lowest point in this landscape because that is the point where model makes least error. Now imagine you are blindfolded and dropped somewhere on that landscape. You cannot see the area, but you can feel the ground under your feet. So how would you find the lowest point? You would feel which direction the ground is sloping downwards and then take a step in that direction. For the next step, you will repeat this again. This is exactly what a model does during training. It cannot see the full picture. It just keeps taking steps in the direction that reduces the loss. Now you will keep moving in the direction which will reduce the error. Now here is another important property that we need to understand, which is gradient. Gradient is the direction that will tell us where the loss increases the most. Now if you know which direction is uphill, you just go in the opposite direction so that the loss can be minimized. Moving in that direction is known as gradient descent. The model uses the gradient to figure out which direction to step in and then moves in the opposite direction to reduce the error. Now we know in which direction we need to move. Next important question is, while moving in that direction, how big each step should be when moving in that direction. This is controlled by something called learning rate. The learning rate will decide how large or small each adjustment is when the model is trying to reduce the loss. If the learning rate is too large, that means model takes huge steps. So if the model takes bigger steps, then there is a high possibility that it might miss the low loss areas. On the opposite side, if the learning rate is too small, that means the model takes tiny baby steps. With small steps, the model will eventually get to the position where loss is minimum, but it will take forever. And in real machine learning, time and computation both cost money. So finding the right balance in the learning rate is really important. Now going back to our parking example, if you overcorrect every time you adjust, you will keep swinging left and right and never park the car. But if you make tiny adjustments that are too small, you will be able to park the car properly, but it will take you the whole day. So you just need the right amount of correction each time. That defines your learning rate. Now here is a tricky problem that comes up in real optimization. Remember that hilly landscape and valleys? What if there are multiple valleys, but some valleys are just small dips, but others are deeper? The deepest point across entire landscape is called global minimum. That is the ideal spot. But sometimes model find a small dip and get stuck there because all the adjacent sides or direction will show increase in the error rate. So that small dip is called local minimum. This is the real challenge in machine learning. The model can get trapped in local minimum and will stop improving, even though there is a better solution out there. There are multiple techniques developed by researchers to help models escape the local minima and keep searching for the global ones. We are not going to dive into that, but the problem itself is something every machine learning engineer has to be aware of. Now, here is another interesting question. Why doesn't a model just learn everything in one go? Why does it need millions of steps? The reason for this is because the error surface is complex. It has hills, valleys, flat regions, sharp drops, all are mixed together. So you cannot jump to the bottom in one step. You have to navigate it slowly and carefully. So due to this, model will learn iteratively. First, it will make a prediction, then it will check the loss, and according to the loss, it will adjust slightly. Now, the model will repeat this multiple times until the model converges. That means the model stops improving much and has found a good enough low point. Now, you might be wondering, we have super fast computers, but still, why does training a large AI model take days? The reason is because the error surface for a complex model is not just a simple 2D landscape. It has millions, even sometimes billions of dimensions, one for every parameter in the model. Navigating that space, including calculating gradient, adjusting parameters, and checking loss, all of this takes huge amount of computation. And it has to be done iteratively because there is no shortcut to finding the lowest point. This is why training GPT level models cost millions of dollars and weeks of time on specialized hardwares like GPUs. Optimization is simple in concept, but at scale, it is one of the hardest problems in all of the computing. Now, let us quickly connect all of this to the heart of machine learning, which is the neural network. A neural network has millions of internal settings called weights. And when you first create the neural network, these weights are basically random. The model is completely useless at that point. Training is the process of using optimization to fix those weights by adjusting them at each step. That is done using gradients and learning rate. It will continue until the model starts making accurate predictions. So that's all about optimization concepts in machine learning. So if you find it useful, don't forget to like, share, and subscribe. And if there is any concept that you want me to explain in detail, let me know in the comment section. In the next video, we will start with calculus, which is required for artificial intelligence. So I'll see you in the next video. Till then, let's keep learning. We keep saying models learn from data, improve over time, and tries to reduce error. But what does that really mean? There is no intelligence present in the model to decide what to do to achieve all of this. There is just a system that keeps adjusting the numbers. So now the question is, how does it know which number to adjust, in which direction, and by how much? And that is exactly where calculus comes in. So let us start with the final piece of math for AI, which is calculus. Calculus is the hidden foundation of artificial intelligence and machine learning. It helps in model training, optimization with backpropagation, and minimizing errors. The end goal is to minimize the error, and for that, we need to calculate the gradient so that we can adjust the parameters for better performance. Calculus provides key tools such as derivatives and chain rule, which are used for deep learning and optimizing accuracy in neural networks. So let us begin with the most fundamental idea, the derivative. Forget the mathematical definition for a moment and think about something very basic. Suppose you are driving a car and your position is constantly changing as you move. But when you are actually driving, you are not thinking about the position. You are thinking about the speed, like how fast I'm going, am I speeding up or slowing down? And speed is nothing but how fast is your position changing. That rate of change is what we call derivative. Now bring that same idea into machine learning. During training, the model makes a prediction. We compare the prediction with the correct answer, and then we get a number that tells us how wrong the model was. That number is the error. Now that error depends on the weights assigned in the neural network. So what will happen if, let us say, you slightly change one weight? What happens to the error? Does it increase or decrease? And how much of that change will be in magnitude? The derivative tells you exactly that. It tells you how sensitive the error is to a small change in the parameter. So instead of thinking of derivative as a formula, you can think of it as a sensitivity measure. If I touch this value, how much does the output will react? Now imagine a curve. On the x-axis you have weight and on the y-axis you have error. So every point on this curve tells you for this weight value this is the error. Now pick a point on that curve and draw a tangent line. That line has a slope, and if that slope is positive, that means if you increase the weight, the error is increasing, and if the slope is negative, then increasing the weight reduces the error. And if the slope is 0, you are at a flat point, which is typically a minimum or maximum. So training a model is nothing but moving on this curve in such a way that you go towards a lower error. You can think of it like standing on a hill in a fog. You cannot see the entire landscape, but you can feel the slope under your feet. If the ground is sloping downwards in a direction, you walk that way. That local slope is your derivative. Now, real models are not that simple. They don't have just one parameter. They have thousands or even sometimes millions of parameters. So instead of a simple curve, now you have a high dimensional surface. Now error depends on many variables, not just one. So now the question becomes, if I change only one parameter and keep all other constant, how does the error will change? This is what we call partial derivative. So for each parameter, you measure its individual effect on the error, assuming everything else stays the same. It is like you have a control panel with many buttons and you want to understand what each button does independently. Now you might wonder, if we have so many parameters, how does we combine all this information? That is where gradients comes in. A gradient is a collection of all these partial derivatives. So instead of a single slope, now you will have a direction in multi-dimensional space. That direction tells you where the error increases the fastest. And since we want to reduce the error, we go in the opposite direction. That process of going in the opposite direction is called gradient descent. You calculate the gradient, move in the opposite direction, update your parameter, and repeat the same process again. Now, till this point, we assume that the relationship between parameters and error is direct. But in neural network, it is not the case. Because in neural network, input goes through multiple layers. In that, it gets transformed at each step and finally produces an output. The error is calculated at the end. So if you change a weight in the first layer, its effect has to travel through all the layers before it impacts the final error. So the dependency is not direct, it is chained. This is where the chain rule comes in. Neural networks rely on complex nested functions. The chain rule of calculus is used in the backpropagation algorithm to determine how changes in early neural network layers affect the output that enables inefficient training of the deep model. The idea is very simple. If A affects B and B affects C, then A also affects C through B. Instead of trying to calculate the total effect in one step, you break it into smaller pieces. You calculate how A affects B, then how B affects C, and then combine them. In neural networks, this becomes extremely powerful. The error depends on the output, and the output depends on the last layer, and the last layer depends on the previous layers, and so on. So, to understand how a weight in early layers affects the error, you propagate the effect step by step through the network using chain rule. This entire process is what we call backpropagation. In this, at each step, you calculate how much each parameter contributed to the final error. So you start from the error, then move backwards layer by layer, computing gradients for each weight. Once you have those gradients, you update the weights using gradient descent. So if we connect these things, derivative tells us how something changes, partial derivative extends that to multiple variables, then gradients combine all these directions after that, and chain rule helps you handle layered dependencies. And in the end, backpropagation uses all of this to update the network weights. Now comes the most important takeaway. A machine learning model does not know what is right or wrong in a human sense. It only knows error, and it only knows how to reduce that error. Calculus gives the model a direction. It tells the model if you move this way, the error will increase, and on the other way, the error will decrease. It also tells how steep that change is, so the model knows how big a step it has to take. So when we say a model is learning, what we really mean is that it is following the direction given by calculus to minimize the error. That is why calculus is not just a part of AI, it is the core mechanism that enables learning. So, just to summarize, we can say that calculus is used to minimize loss function in a model. By taking the derivative of error function, it guides the model towards best weights and parameter combination where error can be minimized. Suppose you are working in a real estate company and your job is to predict the price of a house. Now you look at the data and you notice one very basic pattern. As the area of the house increases, the price also increases. So naturally, your mind tries to connect these two things. You think, can I draw a line that can represent this relationship? That is exactly where linear regression starts. Now let us understand what we are trying to do here. Let us say we have some data points. On one side we have input, which is area, and on the other side we have output, which is price. So our goal is not to perfectly match every point, because that is not possible, but our goal is to draw a straight line that best represent all these points together. That straight line is what we call a linear regression model. Now mathematically we can write it as y is equal to mx plus b. Here m is just the slope of the line, which tells us how much price change when the area changes, and b is the intercept or constant that tells us base value when the input is 0. So the model is simply saying, given for an input x, I will predict the output y using straight line relationship. Now the important question is, how do we decide which line is the best line? Because there are infinite lines we can draw here in this graph. Some lines can be closer to the most points, some will be far away. So we need a way to measure which line represents the main pattern. This is where the cost function comes in. Think of it like this. For every data point or our line, it will give us the predicted value. But that prediction will not be exactly equal to the actual value. So there will be some error or some difference. Now for all the data points, we calculate this error. Error is nothing but the difference between the actual data point and the predicted value which is generated using that line. And to make sure the positive and negative errors don't cancel each other, we first square them and then we add them together. This total becomes the error, which is called cost. So the cost function is simply telling us how far is our line from the actual data. Now our goal becomes very clear. We want to find a line where the cost is minimum. In other words, we want that line that has the least total error. Now comes the next part. How do we actually find the best line? We can't just guess it, right? We use a method called gradient descent, which we have discussed in many of our previous videos. To understand gradient descent, imagine this. Think of a cost as a surface. For every possible line, there is a cost value. So if you plot all the possible lines and their costs, you get a surface that looks like a valley. So at the top, the cost will be high, and at the bottom, the cost will be minimum. Now, what you do is you start from some random line and then you check which direction the cost decreases. Then we take small steps in that particular direction, and we will repeat this again and again. Slowly, step by step, we keep moving downwards until we reach the lowest point. That lowest point gives us the best value of m and b in the equation, and that also means we have found our best line. So now if you connect everything together, linear regression gives us the model, which is a straight line. Cost function tells us how bad our current model is, and gradient descent help us adjust the model to make it better. Now there is another important question. How do we validate if the prediction made by model is actually useful or not for the new data that it will encounter? For that validation, the data set is initially divided into two parts. One is training data, other one is test data. Model will be trained using the training data, and once the line is identified after the training, it will be validated against the test data to see how well it predicts for the newer data set. Now let us talk about where it is used. Linear regression is used in many real problems. Whenever there is a roughly linear relationship between input and output, that means for every consistent change in the input, the output changes at a constant rate. For example, predicting a house prices, forecasting sales, and estimating demands. So basically, whenever you believe that the change in input leads to a proportional change in the output, there we can use linear regression. So this is one of the most basic pattern in the world. That means we cannot use it everywhere. So it cannot be generalized for all. So let us talk about where it fails, because that is more important than knowing where it should be used. First is it will fail when the relationship is not linear. For example, if the data follows a curve instead of a straight line, so in such cases, linear regression will try to fit a straight line anyway and will result in poor model predictions. Second scenario is when it is very sensitive to outliers. So outliers are nothing but the data points that fall far away from the general line which is formed by rest of the data. If one or two data points are very far from others, they can pull the line towards themselves. This can completely distort the model behavior. Third is in real world scenarios, output usually depend on multiple factors, not just one. So linear regression can handle multiple inputs, but it will still assume the relationship between those is linear. So if the real relationship is complex, the model will not capture it properly. Linear regression is simple and powerful. It is mostly the first model you should try. But at the same time, you must always ask a very important question. Is the relationship really linear? Because if that assumption is wrong, the entire model becomes unreliable. Suppose you are working on a banking application and your job is to predict whether a customer will default on a loan or not. Now, here the output is not a number like house price, it's a category. Either the customer will default or they will not. So, now the question is, can we still use linear regression here? At first, it might feels like yes, we can. We can just draw a line and try to predict the values. But there is a problem. Linear regression can give any value. It can give negative numbers, it can give values greater than 1 also. But in case of finding a customer will default or not, the output should be either 0 or 1. So clearly a straight line is not a suitable solution here. So now we need a model that can give output in a fixed range, something that can map any value or any input value into the values between 0 and 1. So this is where logistic regression comes in. Logistic regression is a statistical technique which is used to model the probability of an event occurring based on one or more independent variables. So while your input data can be numeric type, the output is always binary, either 0 or 1. Let us continue with the same example of finding defaulter customers. We will still have inputs like income, credit score, age, but now the output is binary. 0 means no and 1 means yes. So instead of predicting the exact value, we are predicting the probability of belonging to a particular class or category. Now the question is, how do we convert a linear output into the probability? For that, we use a function called sigmoid function. Think of it like this. We still calculate the linear values internally, just like in the linear regression, but instead of using the value directly, we pass it through a function. That function converts any value into a number between 0 and 1. That function is called sigmoid function. So now what happens is, for any input, the model gives probability. For example, 0.8 means high chances of yes, or 0.2 means low chances of yes. Now we need to convert this probability into the final decision. So we define a threshold like usually 0.7. So if the probability is greater than 0.7, we usually say yes. And if it is lower than 0.7, we will say no. Now, the important question here is, how do we train such models? How do we make sure it gives the correct probabilities? Just like linear regression, we need a cost function here as well. But here we cannot use the squared sum just like we used to do in our linear regression, because this is a classification problem. So instead of that, we use something called log loss, or also known as binary cross entropy. It is a loss function for binary classification that measures the performance of a model by calculating the penalty for incorrect probabilities. So, in simple words, it is a way to score how well a model guesses yes or no by punishing the wrong guesses. So, this cost function heavily penalizes the wrong predictions. For example, if the value is 1, but the model predicts the probability close to 0, then the error becomes very high. So the model learns to adjust itself in a way that correct predictions get higher probabilities and wrong predictions get lower probabilities. Now, how do we minimize this error? Again, we will use gradient descent. The idea is exactly the same. We start with the random parameters, we calculate the cost, then we adjust the parameters step by step in the direction where the cost decreases. So if you can connect everything together, logistic regression still uses linear regression or linear equations internally, but it applies a sigmoid function to convert that into probabilities. After that, it uses log loss to measure the error and gradient descent to optimize the model further. Now let us talk about where it is mainly used. Logistic regression is used in all binary classification problems like spam detection, fraud detection, etc. Use cases are very simple and straightforward. Now the important part is, where does it fail? So logistic regression still assume a linear boundary. That means it tries to separate classes using a straight line. So if the actual data is complex and cannot be separated linearly, this model will struggle. Secondly, it does not perform well when there are too many complex interactions between the features. That means the effect of one feature is depending on the another feature, because it cannot capture non-linear relationships. So linear models assume that if you increase the input, the output changes at a constant rate. But many real-world patterns are curves, waves, or sudden jumps. Because these models only see in straight lines, they cannot fit the data that follows a more complex shape. Lastly, it can be sensitive to imbalanced data. Suppose if one class is much larger than the other, the model can become biased towards the majority class. The idea is very simple. Logistic regression is a classification model. It takes the linear combination of inputs and converts it into probabilities using sigmoid function. It is simple, fast, and very useful as a starting point. So till now we have already understood linear regression and logistic regression. In linear regression, what we were doing was trying to fit a straight line to predict a continuous value like price or sales. And in logistic regression, we extended that idea to classification, where instead of predicting a number, we were predicting a probability and then converting it into a yes or no answer. So in both the cases, one assumption was always there. That assumption was the relationship between input and output is linear. Now, the question is, what if the assumption itself is wrong? Because in real world problems, relationships are rarely that simple. Let us take a simple example. Suppose you are trying to approve a loan. Now, the decision is not based on just one factor like income. You might think like this: if the income is high and credit score is good, then you need to approve the loan. If the income is low but the credit score is excellent, then maybe you will still approve it. But if both are low, then definitely you will reject the loan application. Now, if you notice carefully, this is not a straight line relationship. This is more like a set of conditions, and this is exactly the limitation of linear and logistic regression. They try to draw a single line to separate things, but real world decisions are not often that linear, they are rule based. So now the question becomes, instead of fitting a line, can we make decisions step by step using conditions? This is where the decision trees comes in. A decision tree works exactly like how human would think while making a decision. It does not try to fit a formula. Instead, it asks a series of questions. For example, is the income greater than 50,000? If yes, then go one side of the tree. If no, then go on the other side of the tree. Then again, it will ask another question. Maybe, is the credit score above 700? And again, it will go for one answer to the one side, for the other answer to the other side, and this process will continue. So instead of trying to model everything in one equation, we are breaking the problem into smaller decisions. Now the important question here is, how does the model decide which question to ask first? Because we can ask many questions, we can split based on income, age, credit score, and anything. So how does it decide the best split of the questions? To understand this, we need to understand one's concept, which is impurity. At the beginning, your data is mixed, so that will contain some customer which will default, some will not default. So this data set we can say is impure. Now when we split the data, our goal is very simple. We want to create groups that are as pure as possible. That means one group should be mostly containing yes and other one should be mostly containing no. So every split in the decision tree is trying to answer this. After splitting, how pure are the resulting groups? Now we need a way to measure this impurity. For that, we use mainly two concepts, entropy and Gini. So first, let's try to understand entropy. Entropy basically tells us how mixed the data is. So let us say, suppose in our group we have 50% yes and 50% no. It is highly mixed. So we can say the entropy will be very high for this group. And in the same case, if the group has 90% yes and 10% no, that means it is less mixed. So the entropy will be lower in this case. And if in a group it has only either yes or no, then we can say entropy becomes zero. So entropy is nothing but it's like a randomness in the data. So if we only have one option, either yes or no, then we can say the data is completely pure. So while building the decision tree, we try different splits and we choose the split which reduces the entropy the most. This reduction is called information gain. So the model will always try to maximize the information gain. Now let's talk about Gini. Gini is another way to measure the impurity. Just like entropy, it also tells us how mixed the data is. Lower the Gini means more pure data and higher Gini means more mixed data. So in practice, both entropy and Gini give very similar results. The only difference is that Gini is slightly faster to compute. That is why most of the implementations uses Gini. So now if we connect everything together, the process looks like this. We start with the full data set. We try different possible splits. Then for each split, we calculate impurity. Then we choose the split that gives the most pure groups. Then we repeat this process on each group again and again until we reach a point where the data becomes sufficiently pure or we decide to stop. Now let us talk about where the decision trees are mainly used for. What are their use cases? They are very useful in the problems where decisions are naturally rule based. For example, loan approval systems, customer segmentation, or medical diagnosis. Basically, anywhere where you can explain the decision using conditions. Now, the most important part, where does this model will fail? The first problem is overfitting. So decision trees can keep splitting the data until they perfectly fit the training data. But when the new data comes, they fail because they have learned the noise instead of pattern. The second problem is instability. If you slightly change the data, the tree structure can change completely. So the model is not very stable. The third problem is that the trees do not handle smooth relationships very well. So if the relationship is continuous, the trees try to approximate it using step-like splits, which may be inaccurate. So all in all, we can say that the decision trees are very intuitive. They match how we human think. They break complex problems into smaller decisions. But at the same time, they can overfit and become unstable. And that is exactly why we usually don't rely on a single tree. Now we have understood decision trees and before that linear and logistic regression. And if you look carefully, there is a clear progression in how we are solving the problem. In linear and logistic regression, we were trying to capture the relationship using single line, which works well when the relationship is simple and linear, but starts failing when the data becomes more complex. Then we move to decision trees, where instead of forcing a single equation, we started breaking the problem into smaller decisions by asking questions step by step. And this worked much better for non-linear and rule-based problems. But decision trees introduced a new problem. The problem is that decision trees are very sensitive and unstable. So if you slightly change the data, the entire tree structure can change because the splits depend heavily on the data set. Also, decision trees have a strong tendency to overfit. That means they try to perfectly lean to the training data that also includes noise, which can lead to the poor performance to the new data. So now the question becomes, how do we keep the power of decision trees but reduce the weaknesses like overfitting and instability? So this is where random forest comes in. So instead of relying on a single decision tree, random forest creates multiple decision trees and combine their output to make a final decision. So instead of trusting one single model, we are taking a group opinion. Now think about this as a real world scenario. If you ask one person for a decision, that person might be biased or might make a mistake. But if you ask 100 different people and take the majority vote, the final decision is usually more reliable. So random forests work in the exactly same way. So now the next question is, suppose even if we are creating multiple trees, now because they are trained on the same data, won't they become exactly same? So this is where the random part comes in. Random forest introduce randomness in two ways. The first is instead of training each tree on the entire data set, it takes a random subset of that data. This is called sampling with replacement, also known as bootstrapping. It is a statistical resampling technique that involves drawing multiple samples of size, let's say n, from a single original data set where each data point is replaced back before the next draw. So each tree sees a slightly different version of the data. Second way is while creating the splits, instead of considering all the features, each tree consider only a random subset of features. So because of these two reasons, each tree becomes slightly different from the others. Still, some trees might make mistakes, but their mistakes will be different. Now, when we combine all these trees together, the error tends to cancel out and the overall model becomes more accurate and stable. So now if you connect everything together, the process may look like this. We create multiple datasets by sampling from the original data. Then we train a decision tree on each dataset. While splitting the dataset, each tree uses a random subset of feature. And finally, for the prediction, we take the output of all those trees. So we saw earlier that linear regression and logistic regression had limitations, but using random forest, we can overcome those as well. For example, for classification problems, we can use majority voting of multiple trees. And for regression problems, we can take the average of all the predictions. Now let us talk about where random forest is actually used. Random forest is used in a wide variety of real world problems. For example, fraud detection, recommendation system, risk analysis. So basically, anywhere where you need a strong and reliable model without too much of tuning. Now comes the important part. Where does random forest fail? So with a single decision tree, you can easily understand the logic. But with hundreds of trees, it becomes difficult to explain how the final decision was made. So it becomes less explainable. Secondly, the training process of multiple trees takes more time and resources compared to a single tree. So it becomes more computationally expensive, and in any industry, the only motive is to make and save as much as possible. Also, if the data is extremely large or requires real time predictions, the random forest might not always be the best choice due to its complexity. So, the key idea in random forest is very simple. Random forest takes a weak and unstable model like a decision tree and make it strong and stable by combining multiple trees together. It reduces overfitting, improves accuracy, and gives better generalization. And on top of all, this introduces a very important concept in machine learning, which is instead of building one perfect model, we can combine multiple simple models to create a powerful one. This idea is also called ensembled learning, where we combine multiple individual models called weak learners to create a single, stronger, and more robust predictive model. And random forest is one of the most popular example of it. K-nearest neighbor or KNN is a machine learning algorithm that is mainly used for classification and regression work. In this, we identify a fixed number of closest data points for a particular input, and then based on the majority class, we provide the prediction. Here we classify the data based on their nearby points. That is, if a group of data points are nearby to each other, then they will be classified, or we can say grouped together as one category. Till now, we have seen a clear pattern in how the models work. In linear and logistic regression, we were learning a mathematical equation from the data. In decision trees, we were learning a set of rules by splitting the data. And in random forest, we improved those rules by combining multiple trees together. So, in all of these approaches, one thing was common. We were training the model first and then using the trained model to make the prediction. But what if we don't do that? What if instead of making the model learn in advance, we simply store the data as it is? And whenever a new data point comes in, we compare it with the existing data and make a decision based on similarity. So that is the exact idea behind KNN. Now, to identify the nearest neighbors, there are different metrics we can use. One simplest metric is Euclidean distance. Other than that, we have Manhattan and Minkowski distance as well. This algorithm is also known as lazy learner algorithm because unlike other algorithms, it does not learn from any training set. It stores the data set and then compute only at the time when classification is done. This algorithm predicts the category of new input data point based on the closest neighbor category. Now, suppose there are existing data points in the space with two clear categories. One is denoted as circles and others as triangle. So, if this new data point comes in, then as per KNN algorithm, distance between the neighbor data points will be calculated. As this new data point have majority of nearest data point from triangle, so the new data point also belongs to the triangle category. From this, one thing is clear. This algorithm depend on mainly two factors: close data points and majority voting. Now here is an important question. What do you mean by K in KNN? K is just a number of data points nearby that we need to look for while making a prediction. Now suppose you need to predict the type of fruit based on its shape and size. For the input fruit, you compare these properties with the fruit's data point you already have. Suppose if the K is 5, then algorithm will consider 5 closest fruits to the input. Now if three or more fruits are of the same category, then the algorithm will categorize the new fruit with the same category. But how do we decide the value of k? Like how many data points to compare while making a prediction? Because this number plays an important role in predicting the outcome, it becomes critical to select the correct value of k. Suppose if the data has too much of noise, that is, it is difficult to identify the clear patterns, then we can use larger value of k to make it more stable. But if we use large value of k, then it can cause underfitting, where it can start considering the noise as well and miss the real patterns. Now there are few ways using statistics using which the value of k can be selected. The first simplest approach is using odd values. So for classification problems, we use an odd number for k. This helps in avoiding the ties in voting. But this will only gives us a number of values which we can select from and not the exact value. So for that, we can use either cross validation or elbow method. In cross validation, data is divided into k parts and then the model is trained on some of those parts. Now to validate, the remaining part will be used. Now this process is repeated for all the parts, and whichever k value gives the highest accuracy during validation, that will be used as value of k. In case of elbow method, we draw a graph that either shows error or accuracy for different values of k. So as we increase the value of k, the error value usually drops at first, but after a certain value of k, the error value stops decreasing. So at this point, the curve will change the direction. It is the best fitting value of k. Now we know how to select the value of k. let us understand how we will measure the distance to mark the nearest data points. So as I mentioned earlier, there are mainly three ways: Euclidean, Manhattan, and Minkowski distances. Euclidean distance is a straight line distance between 2 points in Euclidean space. It is calculated as the square root of sum of squared differences between their coordinates. It represents the shortest possible path, and it is most common way used in machine learning. The second way is Manhattan distance. This is not the straight line distance between 2 points. In this, starting with the 1 point, we can move either horizontally or vertically. This is also known as L1 distance. So if you remember in one of the previous videos where we have covered norms, there was L1 norm, which tells us how to measure the distance in a grid-like path. The same technique is used to find the Manhattan distance. Third and the last one is Minkowski distance. It is not a single way of finding the distance. It includes both Euclidean and Manhattan distances. Now here, depending on the value of p in the equation, it can act both as Euclidean and Manhattan distances. Now we know how to select the value of k and how to mark the nearest data points. Let us just understand the complete flow and working of KNN algorithm. So it all starts with selecting the number of neighbors, which is the value of k. So before running the algorithm, we must select the value of k. This represents how many neighbor or nearby points the algorithm will look in to make a decision. So if k is 3, the algorithm looks at the 3 closest point, and if k is 5, then it will look for the 5 closest points. The second step is to calculate the distance. So whenever a new unseen data introduced, then the algorithm calculates the distance between new point and the every other point in the training data set. The most common way to do is Euclidean distance, but depending on the nature of data, other ways like Manhattan or Minkowski can also be used. Now, after calculating the distance, algorithm sorts them in the descending order to identify the top k data points. So these k number of points are physically closest to the new input or the query data input. Now, as the last step, we turn all this into a democracy. We will use voting or average to make a decision. Voting will be done if it is a classification problem, and average will be considered if it is a regression problem. In voting, algorithm will see which class has more number of data points which are nearby, which is also known as majority voting. And depending on that, the input point will also be assigned the same class. In case of regression, the algorithm takes the average value of all those k points to predict the value of input data point. Now let us see a few advantages, disadvantages, and use cases of KNN algorithm. KNN is simple and easy to understand and implement. There is no training step required. It just stores the data, uses it at the time of prediction. It works well for both regression and classification problem. Now it does have few disadvantages as well. Like if the data set is very large, then it becomes very slow because then it needs to do a more number of comparisons. Also, it can struggle with where there are many features with different scales. For example, if we have two features like salary and age of an employee, and definitely there will be a huge difference between the values of salary and age. So generally algorithm will ignore the small value changes as compared to the larger value changes. That can make it completely ignore the age feature. For that, we may need to normalize the data first, and that also adds up to the complexity. Now, coming to the use cases, it can be used in the recommendation systems, spam detection, speech recognition, and customer segmentation kind of tasks. Okay, so that's all about KNN. Let me know in the comment section if you have any queries. So now, till this point, we have seen different ways of solving problem. Some models try to fit equations, some try to build rules, and some rely on similarity. Support vector machine is another algorithm used in machine learning. It is mainly used for classification and regression problems. Mostly it is useful when we need classification for binary categories. We know that kind of problem can be solved using linear or logistic regression, where we separate the categories by a line in the space. Now it is possible that there can be multiple lines which can divide that data points. But in SVM, we try to find the best line that separates those categories. But how do we define what is best? Suppose this is the space with all the data points. Now here SVM tries to find a boundary that has maximum margin. Margin is the distance between boundary and the nearest data points from both classes. So imagine you draw a line that separates two classes. Now look at the closest point from each side. The distance from those points to the boundary line is the margin. The main motive of SVM is to maximize this margin because with this, the model will be more confident while doing any prediction. You might be wondering what is the meaning of support vector in this. You see these closest point to the hyperplane from both the classes. These are known as support vectors. So even if you remove other points which are far away from the boundary, the model does not change much. But if you move these support vectors, the boundary also moves. That is why the algorithm is called support vector machine, because these vectors are supporting, or we can say defining, the boundary. Hyperplane in this data space is an area that divides both the classes into halves. That area itself has two boundaries, positive and negative hyperplane. These are like the gutters on the sides of the road. They sit on the very edge of each group. The space between these two gutters is the margin, and the hyperplane sits perfectly at the center of this space. Now, even the margin is also of two types, hard margin and soft margin. A hard margin is the one with maximum value margin, which separates the data without any issue. And soft margin, on the other hand, allows some misclassification for the data, which is not perfectly separable. Now, let us understand how does SVM actually work. The main goal in SVM is to identify the hyperplane with maximum margin, and that margin is the distance between hyperplane and support vectors. The best hyperplane is considered the one with the highest margin, which is also known as hard margin. Now, with hard margin, the separation between classes is very clear. Suppose these are the data points in the space. One is blue class and other one is red class. Here L0 and L1 are the positive and negative hyperplanes, also known as gutters. And here we have L2 in the middle, which has the maximum distance from both the support vectors. Now here you can see the hard margin is possible because we can classify both the classes clearly without any misclassification. What if the data looks like this? Here we have some outlier data points from one of the class. So SVM will ignore the outlier and find the best hyperplane with maximum margin, which is also known as soft margin. But in addition to ignoring that outlier, soft margin will try to minimize the penalty due to misclassification. The penalty is used for misclassification is known as hinge loss. So if the data point is correctly classified and also within the margin, then there is no penalty, which means hinge loss is zero. But if the data point is either misclassified or not in the margin, then the loss will be according to the distance between correct classification. Now, all of this is good and applicable only if we can separate the data linearly. But the real data is mostly non-linear. So in such cases, SVM uses a technique called kernels. In this, instead of trying to separate the data into same space, we transform the data into a higher dimensional space. In this new space, the data might become separable. This transformation helps SVM find a decision boundary even for the non-linear data. A kernel, we can say, is a function that maps the data point into a higher dimensional space without computing the coordinates in the space. This allows SVM to work with nonlinear data as well. Now, based on the type of boundary, SVM is broadly classified into two types, linear and nonlinear SVM. As the name suggests, linear means the data can be classified using a straight line, and nonlinear is when the higher dimensional transformation is required. Support vectors are very good at classifying higher dimensional complex data using flexible nonlinear boundaries. With all of this and still remaining memory efficient. But just like other algorithms, it also have some drawbacks. SVM is not good for large and noisy datasets because it slows the training speed, very difficult to perform parameter tuning, and it is very sensitive to the feature scaling. Now, if we connect everything together, SVM tries to find a boundary that separates classes, but instead of just separating, it maximizes the margin. Only a few points called support vectors define this particular boundary, and when data is not linearly separable, it uses kernels to handle the complexity. Now, till this point, we have covered a wide range of algorithms, each one solving problems in a different way. But in real world scenarios, the model is only one part of the system. What actually matters is how the data is prepared before it even reaches the model, because even the best model will fail if the data is not handled properly. So, in the next part, we will focus on how data is processed and prepared. So, till now, we have spent a lot of time understanding different machine learning models. Now, if you think about it, all these models are very powerful. Each one is capable of solving complex problems in their own way. So, naturally, you might think if I choose a good model, my problem should be solved. But this is where most people make a mistake. In real world machine learning, models are not the biggest challenge. The real challenge is the data. Because no matter how powerful your model is, if the data is not prepared properly, the model will definitely fail. And not just fail, sometimes it will give results that may appear correct but are actually wrong. So there are multiple examples of bad data. Your data may have missing values, or maybe what if one feature has values in thousands and other one is in decimals, and many more other reasons. All these problems happen before the model even starts learning. And if they are not handled properly, the model will learn the wrong patterns. So from this point onwards, we will shift the focus from building a better model to preparing the data in the right way. Because in machine learning, a well prepared data set with a simple model will always outperform the complex model with the poorly prepared data. And if you ever deployed a model that worked perfectly fine in testing but completely failed in production, you will know exactly what I'm talking about. So let us start understanding how data is actually handled before it reaches the model. The first thing to understand is why and how should we split the data. We should not train the model on entire data set. We need to divide the data set for different purposes. Suppose you have a data set and you use the entire data set to train your model. After training, you check the performance on the same data and you see that the accuracy is very high. Now, the question is, can you trust this result? The answer is no, because the model has already seen this data during training. So it is not really predicting, it is just remembering. This is similar to a student who practice only one set of questions and then gets the same question in the exam. And of course, his test score will be high, but that does not mean the student has actually understood the concepts. So, to properly evaluate a model, we need to test it on the data that it has never seen before. And that is why we split the data. But here is something important. When you split, you need to maintain the distribution of your target variable. For example, if you are predicting loan defaults and only 5% of your data contains defaults, you cannot randomly split and end up with all the defaults in training and none in the test data. This is called stratified splitting, and it ensures each split has the same proportion of each class. Most libraries handle this automatically, but it is crucial to know why it is important. We typically divide the dataset into three parts: training data, validation data, and test data. So let us understand each one. Training data is used to train the model. This is the data from where the model learns the pattern. It adjusts its parameters and tries to reduce the error. Validation data is used during training to evaluate the model. We use it to tune hyperparameters. Hyperparameters are the external configuration settings which are used to structure and control the learning process of a model. It is usually set by the user before training begins. For example, choosing the right value of k in KNN, or choosing the depth in decision trees. It helps us compare different versions of the model. Other than this, we have test data. It is used at very end and only once to get the final performance of the model. Think of it like this. Training data teaches the model, validation data helps you make decisions about the model, and test data tells you if those decisions which you have made using the validation data are right or not. For smaller data sets, you might skip the validation set and use something called cross validation instead. But the test set, that is non negotiable. Now, one important thing to understand here is the model should never see the test data during training, because the moment it sees the test data, it is no longer a fair evaluation. So, if we connect all of these things together, the flow may look like this. We train the model using training data, then we tune and improve it using validation data, and finally, we evaluate the model using test data. This may look very simple on the paper, but here is where things get tricky in real projects. And one of the most dangerous mistake is data leakage. Data leakage happens when your model gets access to the information that it should not have during the training, especially the information from test dataset. Now, at first, this might sound like an obvious mistake. You might think, I will never train my model on the test data. But in real scenarios, leakage does not happen directly. It happens in very subtle ways. Let me show you how it is actually happening. Suppose you have a data set and before splitting, you decide to do some pre-processing. For example, you calculate the average of a feature and fill the missing values. Now, if you calculate this average using the entire data set, you are indirectly using the information from test data set. So even though you did not explicitly train on test data, the training process already is influenced by that. And this is one of the forms of data leakage. The main problem is that it gives you very good results. Your model will show very high accuracy and everything will look perfect. But when you deploy it on the real world, the performance will drop suddenly. Because in real world, that leaked information is not available to the model. So your model can no longer cheat. This happens because your model was never truly learning from the real pattern. So how do we prevent this data leakage? Here are three rules that will save you. First is always split the data before doing any pre-processing. Secondly, any operation like scaling, encoding, or filling missing values should be done using only the training data. And then the same transformation should be applied to the validation and test dataset. Third is always think from a deployment perspective and ask yourself, will this information be available when model is actually used? If the answer is no, then it should not be part of the training dataset. So if you can connect this with whatever we have discussed earlier, splitting the data is not just for evaluation, it is also for protecting the model from leakage. Now, once the data is properly split and protected, the next step is to clean that data. So now let us understand the most basic cleaning step, how we handle the missing data. In an ideal scenario, every row in your dataset should have values for all the features. But in reality, that almost never happens. You will always have some values that are missing. Maybe a user did not fill the field, or maybe a system failed to capture it, or maybe the data was not available at that time. So now the question is, what should we do with these missing values? Can we just ignore them? The answer is no, because most machine learning models cannot handle missing values directly. If you try to train a model with missing data, it will either throw an error or give incorrect results. So we need to handle them properly before training. We have multiple approaches for that. The first and simplest approach is to remove it from the data. If we have very few number of rows which are having missing values, we can drop those rows. But this works only when the missing data is very small. If a large portion of data is missing, removing rows can lead to loss of important information as well. So in that case, we need another approach. The second approach is to fill the missing values. This is called imputation. But what should be the values that we fill and that also make sense? For numerical data, a common approach is to use mean or median. Mean works well when the data is evenly distributed, and median works better when there are outliers. For categorical data, we usually fill with the most frequent values. But here is something important to understand. When we are filling the missing values, we are making an assumption. We are saying that the missing value is similar to the average or the most common case. This is not always correct, and if we are not careful, it can introduce bias in the model as well. So there is another approach where we create a separate category or indicator for missing values. For example, instead of filling, we can add a flag column that tells whether the value was missing. This sometimes helps the model understand that missingness itself carries some information. And this brings us back to our golden rule. All these operations should be done using only training data. For example, if you are calculating the mean to fill the missing values, you should calculate it only on the training data and then apply the same validation to test data as well. If you calculate it using entire dataset, you are already introducing data leakage. So just to summarize this part, missing data is very common. We either remove it or we fill it. But every method comes with assumptions, and we must apply those steps carefully to avoid data leakage. Now, once the missing data is handled, the next challenge is that not all data is in numerical form. So now let us understand how do we convert categorical data into a format that a model can understand. If you look at the real world dataset, many features are categorical. For example, city name, product type, user categories, payment methods. These are not numbers, these are labels or categories. Now, the problem is that most machine learning models work with numbers. They cannot directly understand text or categories. So, the challenge here is how do we convert this categorical data into numerical format without losing its meaning? Now, here is a very simple idea. We can assign numbers to each category. For example, red will be assigned 1, blue will be 2, green will be 3. This is called label encoding. It is simple and easy to apply, but there is a problem. When we assign numbers like this, the model may assume an order. It might think that the blue is greater than red or green is greater than blue. But in reality, these categories have no order. So we are introducing a relationship that actually does not exist. This can definitely confuse the model. This approach works only when the categories have actually natural order in them. For example, we have low, medium, high, and then we give them numbers in that particular order. So in such cases, label encoding makes sense. But for categories that are just labels with no ranking, we need a different approach. And that approach is called one hot encoding. In one hot encoding, instead of assigning a single number, we create a separate columns for each category. For example, if we have these three categories, red, blue, green, we create three columns. So here, if the number is red, then red will be 1 and all other will be 0. And if it is blue, then blue will be 1 and all others will be 0. So for each data point, only one column will have value 1 and rest will have value 0. Now, if you notice, this removes the problem of ordering. All categories are treated equally now. There is no false relationship. But this also introduces a new issue. So if the number of categories is large, then the number of columns will also increase. This can make a dataset very large. So we need to be very careful when using one hot encoding for high cardinality features. And here is one more important point. Just like missing data handling, encoding should also be done using only training data. For example, if a new category appears in the test dataset that was not present in the training data, we need to handle it properly. Otherwise, it can break the model. So, just to summarize this part as well, categorical data cannot be used directly. We convert it into numbers using encoding. Label encoding is the simplest one, but it can introduce wrong relationships. To fix that issue, we can use one hot encoding, but that can increase the dimensionality. Now, once all the data is in numerical form, there is still one important problem left. Different features can have very different scales, and this can affect how a model learns. So now let us understand why feature scaling is important. Suppose you are building a model to predict house prices and you have two features. One is area, which can be in thousands, and another one is number of rooms, which is usually between 1 to 5 or maybe maximum till 10. Now, if you look at these two features, their ranges are very different. One is large and other one is very small. Now, the question is, will this different affect how a model will perceive the patterns? The answer is yes, especially for certain algorithms. Let us take gradient descent based model like linear regression or logistic regression. In those models, we are trying to minimize the error by adjusting parameters step by step. This adjustment depends on how the cost function behave with respect to each feature. Now, one feature has very large value. Its impact on the cost function will also be large. So during training, the model will give more importance to that feature which is having large value. Not because it is more important, but simply because its scale is larger. This can lead to inefficient learning, and the model may take even longer to converge, or maybe not even converge properly at all. Another issue is the path taken during optimization. So instead of moving smoothly towards minimum, the model may take a zigzag path because different features are influencing the updates unevenly. So to fix this, we bring all features to the similar scale. This process is called feature scaling. Now, there are two common ways to do this. First is min max scaling. In this method, we convert all the values into a fixed range, usually between 0 and 1. So, the smallest value will become 0 and the largest value will become 1. Second one is standardization. Here, we transform the data so that it has a mean of 0 and standard deviation of 1. This helps in centering the data and reducing the variance differences. Now, the big question here is which one we should use out of these two approaches. So min-max scaling is useful when we want values in a specific range, and standardization is more commonly used when data has outliers or when using algorithms like SVM or logistic regression. So distance-based algorithm like KNN and K-means also need standardization because they literally calculate the distances between the points. Now, one important thing to remember here is scaling should always be done after splitting the data. And the scaling parameters like mean, standard deviation should be calculated only on the training data set, as we have discussed multiple times in this video. Then after doing that, it's the same will be applied to the validation and test data. Otherwise, we again can introduce data leakage. So if you connect everything together, before training any model, the first step is to properly split the data. Because without a correct split, we cannot truly evaluate the model. Then we need to make sure there is no data leakage, because even a small leakage can give misleadingly good results and completely break the model in real world scenarios. After that, we handle missing data, because real world data is never perfect and models cannot work with incomplete information. Then we convert the categorical data into numerical form, because machine learning models understand numbers, not labels. And finally, we scale the features so that all inputs are on the similar range and model can learn efficiently. Now at this point, we have cleaned the data, handled missing values, converted categorical data, and scaled the features. So now the data is finally ready to be used by a machine learning model. And
Till now, we have understood many algorithms and multiple other concepts which helped us improving the model's learning path. One thing is clear by now, which is models identify the pattern from the data that we provide it, and based on that, it starts predicting next outcome. So we can say the model is only as good as the data. We prepare the data, we clean it, we engineer features, we decide what matters, and then we hand it over to the algorithm. Now what if we do not provide labeled data and the models automatically identify the patterns? Everyone was thinking, maybe this is not even possible. Then they took inspiration from how the human brain works. Human brain has billions if neurons connected with each other. This is the basic structure of human brain's neuron. Don't worry, we'll not go in bio-level details here. Here we have 3 high-level components. First are these inputs, also known dendrites. They receive electrical signals from other neurons and pass it to the main processing unit, which is this nucleus. Now, if the combined signal received from other neurons is strong enough, then it transmits its own combined and processed signal to the next set of neurons. And if the signal is not strong enough, then it doesn't fire. That means nothing goes out of that particular neuron. This sending the signal further or not sending anything is similar to 1 and 0. A single neuron doing this is completely useless, because one neuron can't think, it can't recognize a face or understand a sentence. But billions of them connected together, each one responding to signals from thousands of others, that is something special. The intelligence isn't in any single neuron. The intelligence is in the connections and the pattern of which neurons talk to which others. So the overall idea was, can we model this? Can we build an artificial version of this in software and get something that learns the way we do? And that is how an artificial neural network was born. Now let us understand in detail how an artificial neuron works. So similar to the neuron of the brain, the artificial neuron will have 3 high-level parts, multiple inputs from other neurons, processing unit and output to other multiple neurons. Now imagine we have a neuron that receives 3 inputs. So let's call them x1, x2, and x3. These inputs could be anything. It can be pixel values from an image or numbers from a spreadsheet. Now we need to understand that not all inputs are equally important. Think about it biologically. Some connections in your brain are strong, so when that neuron fires, it really affects you, but other connections are weak and a signal comes in, but it barely makes any difference. To mimic the same behavior in our artificial neuron, we use weights. Remember these weights, they are the core to neural network and plays the most important role in predictions. I have already covered weights on high level in one of Math for AI videos. If you want to learn in depth, you can check it out from the playlist. So we have inputs x1, x2, x3, and corresponding to their forward connection, the weights are w1, w2, and w3. So each input gets multiplied by a weight. x1 gets multiplied by w1, x2 by w2, and x3 by w3. Now if w1 is large, that means input x1 has a big influence on this neuron. If w2 is very small, maybe almost 0, then x2 barely matters. In the next step, we add them all. w1 times x1 plus w2 times x2 plus w3 times x3. We also add something called a bias. It is a constant term that gives the neuron a bit of flexibility. You can think of it as the neuron's default tendency, i.e., before it even sees any input, how naturally activated is it. I may be using a lot of terms like bias, weights, gradient, and many more. And if you are hearing it for the first time, I would recommend you to watch the previous videos in this series before continuing with this. I have already covered what is required to understand all these in better way. So you can go ahead and check out the previous video and then come back later to continue with this video. If you are already aware of all those concepts, then it's is great, so let's continue. Now, after adding the multiplications of weights with inputs, we have a number known as weighted sum. After this, we pass that weighted sum through an activation function. Remember how the biological neuron only fires if the signal is strong enough or crosses a threshold. The activation function does something similar. It takes our weighted sum and transforms it. The simplest version is called a step function. If the sum is above 0, output 1. If it's below 0, output 0. But in practice, we use smoother functions. For example, the sigmoid function, it takes any number and transforms it to a number between 0 and 1. We also have ReLU, which stands for rectified linear unit. In this, if the value is positive, keep it as is, and if it's negative, then make it 0. Activation function is one of the most critical part of artificial neuron. Without it, our neuron is just doing linear math. And no matter how many neurons you chain together, if they're all just doing linear operations, the whole thing is still just linear math. The activation function introduces nonlinear behavior, which is important for network to learn complex patterns. So our artificial neuron takes inputs, multiplies each one by a weight, adds them all up with a bias, and passes the result through an activation function to produce an output. Similar to the biological neuron, a single artificial neuron is still not much useful. The real power comes from connecting many of them together in layers. This is the structure of a neural network. This is the basic structure of a neural network where we have main 3 components. First is input layer. From this, the input data enters the network. Then we have one or more hidden layers, which mainly process the information and pass it on to the next layer. In the end, we have the output layer, which contains the final output. Let us take the classic example of a network that can recognize handwritten digits. So the input to our network is an image. Let's say it's 28x 28 pixels. In total, that gives us 784 pixels, where each pixel has a brightness value between 0 and 255. Value 0 means complete dark, and 1 means complete bright. So our input layer has 784 neurons, one for each pixel, and each neuron just holds the brightness value of its corresponding pixel. There is no computation happening here. This layer is just where the raw data enters. Now, after the input layer, we will have one or more hidden layers. Suppose our first hidden layer has 128 neurons. So every single neuron in the input layer is connected to every single neuron in this hidden layer. That means each of those 128 neurons is receiving signals from all 784 input neurons, and also each connection has its own weight. Now each neuron starts the computation. First, they will add all the weighted sum and then add bias value on top of that. Whatever is the result of this computation, that will be passed to the activation function. Now activation function will decide what will be the output for next layer. All the learning happens in the hidden layers, but in a gradual manner. The first hidden layer may learn very low-level patterns. So in our example, it may learn to detect things like a horizontal edge or a vertical edge. These are extremely basic building blocks, just edges and lines. Now let's add a second hidden layer, maybe with 64 neurons. This second layer takes the outputs from the first layer as its inputs. Now it's working with edges and lines, and it's starting to combine them. It learns things like 2 curved lines meeting a certain way probably means the top half of a digit. A vertical line next to a curve might be part of a 4 or a 9. This layer is learning shapes, which is the combinations of the low-level features. And if we had a third hidden layer, it would combine shapes into even higher level ideas, maybe first parts of digits and then the whole digit structures. We can have multiple hidden layers. If the number of layers are more, then the network can understand the complex patterns too. For a simple digit recognition, not many hidden layers will be needed. So here we have the final layer, which is the output layer. Here the output layer has 10 neurons, one for each digit. Each output neuron produces a number between 0 and 1, which represents its confidence score. So if neuron 0 says, I am 3% confident that the number is a 0, and another neuron 5 says, I am 94% confident that the number is a 5, then we'll pick the neuron with the highest score that will become our prediction. So here the information flows in one direction from left to right, that is, from input through hidden layers to output. And this flow is known as the forward pass. Till this point, the weights are completely random. We haven't taught this network anything. So if we run an image through this network right now, it may produce garbage output. So let us understand, how does a neural network learns? Learning in a neural network happens through training. Suppose we show the network an image of a handwritten 5. We know the correct answer is 5. Next, we run a forward pass. The data flows through the network, starting with input, weighted sum, activation function, and in the final layer it produces an output. For the very first time, most probably the network will say something garbage. Maybe it says, it is a 3. That's wrong, but that's okay, because we know the weights are all still random at this point. And now comes the most important part of the training. Now we measure how wrong the output is. For that we use a loss function, also sometimes called a cost function. The loss function compares what the network predicted, which was 3, against what the answer actually is, which is 5. And based on that comparison, it will give us a number. If that number is big, that means we were very wrong, and small number means we were close, and obviously 0 means perfect prediction. So the main goal of training is to make this loss as small as possible. Now we have the error and we need to pass that error back in the previous hidden layers. That process is known as backpropagation. Now we know we got the wrong answer, and the wrong answer happened because of the weights. The specific combinations of weights pushed the network toward 3 instead of 5. So we need to understand which weights were responsible, and by how much should we adjust those weights to reach the expected outcome. For that, the network uses calculus, specifically derivatives. That part is also covered in my Math for AI video. You can check it out if you want. So now we start from the output where the error is and we move backwards through the network, layer by layer. At each step, we calculate how much each weight contributed to the final error. The final result is a gradient for every single weight in the network. You can think of a gradient as a direction that tells in which direction the error is increasing. Now we adjust the weights in the opposite direction using gradient descent. We take each weight and we change it slightly in the direction that would reduce the loss. If increasing the weight makes the loss go up, then we decrease it a little. And if increasing it makes the loss go down, we increase it a little. The change in weight is controlled by learning rate. It is an important hyperparameter. If the learning rate is too big, we may overshoot and never reaches the optimal loss value. But if it is too small, then the learning will take forever. Now with the updated weight values, we start the process again. This is repeated thousands or maybe millions of times. After those iterations, the weights stop being random. They've been changed so many times that they've settled into values that actually make the network good at predicting the correct value. The network has learned. And here's what's amazing, nobody told it what to look for. Nobody said look for edges in the first layer or combine shapes in the second layer. It figured that out by itself, just by seeing examples and adjusting weights to reduce error. The network learns the structure from data and not from us. Now let me just summarize what we have discussed today. At the beginning of this video, we said, models are only as good as the data we give them. We spend a lot of time preparing data, labeling examples, engineering features. Neural networks don't eliminate the need for data, you still need data. But what they changed is, who does the feature engineering? With traditional machine learning, that was us. We decide which features to use, which features to combine. We bring our domain knowledge and make deliberate choices about what the model should see. With neural networks, it starts with raw data, and it discovers its own internal representation of that data. Layer by layer, it builds up an understanding of what features matter. For images, it discovers edges, then shapes, then objects. For text, it discovers letter patterns, then words, then grammar, then meaning. Nobody programmed any of that, it emerged from training. I hope now you are clear about complete idea of artificial neural network. Now we know how an artificial neuron works. We saw that it takes multiple inputs, multiplies them with weights, adds a bias, and produces a weighted sum. That weighted sum is then passed forward in the network. Now, if you think about it carefully, till this point whatever we are doing is just simple math. We are multiplying numbers, adding them, and passing the result. So if we keep adding more neurons and more layers, will the network automatically become powerful? At first, it might feel like yes, more layers should mean more learning capability. But the reality is a little different. Even if you add hundreds of layers, if every neuron is only doing linear operations, the entire network will still behave like a simple linear model. And that means it will not be able to learn complex patterns. It will only be able to learn straight-line relationships. So we need something that can break this linear behavior. And that is where activation functions come in. After calculating the weighted sum, instead of directly passing that value forward, we pass it through a function. That function decides what should be the output of that neuron. Now this is not just a random transformation. This step introduces nonlinear behavior into the network. And that is what allows the network to learn complex relationships. Now to understand this better, let us look at some commonly used activation functions. The first one is sigmoid. It takes any input value and converts it into a value between 0 and 1. So no matter how large or small the input is, the output will always be within this range. Because of this behavior, sigmoid is very useful when we want to represent probability, like in binary classification problems. Imagine you are building a model for a football game which predicts whether a player will score a goal or not. Now, before calculating the final output, the model considers things like distance from goal, angle, and defender pressure. Suppose the raw output looks like this. Shot 1 has a score of -4. Shot 2 has a score of 0. Shot 3 has a score of 3. But this data is a little confusing and does not clearly tell us what will happen. So we apply the sigmoid function to this raw data. After applying the sigmoid function, we get probabilities like this. Sigmoid -4 is approximately 0.018, which means a very low chance. Sigmoid 0 is 0.5, which means a 50-50 chance. Sigmoid 3 is approximately 0.95, which means a very high chance. Now it becomes useful. Shot 1 has only a 1.8% chance, so we can safely say that if the player opts for that shot, he will not be able to score the goal. Shot 2 has a 50% chance, so we can say that the outcome is uncertain and could go either way. Shot 3 has a 95% chance, so we can say that if the player takes that shot, he will almost certainly score the goal. But sigmoid also has a limitation. When the input becomes very large or very small, the output becomes almost constant. It gets very close to either 0 or 1. And when that happens, the gradient becomes very small, which means the learning slows down significantly. If we consider the same goal prediction example, suppose the raw scores given by the model are extreme like this. Shot 1 has a score of. Shot 2 has a score of 0. Shot 3 has a score of 10. After applying the sigmoid function, we get sigmoid -10 is approximately 0.00004, which is almost 0. Sigmoid 0 is 0.5, which is normal. Sigmoid 10 is approximately 0.99995, which is almost 1. That means shot 1 has only a 0.004% chance, so we can say that the player will definitely not score the goal. Shot 3 has a 99.995% chance, so we can say that the player will almost certainly score the goal. Now no matter how much you change the input, if it becomes -20 or -50, the output will still remain close to 0. If 10 becomes 20 or 50, the output will still remain close to 1. The model learns using gradients, which is another name for slopes. But in these extreme regions, the sigmoid curve becomes flat and the slope becomes almost 0. Very small gradient means very tiny weight updates, which leads to very slow learning. Now let us look at another function, which is ReLU. ReLU stands for rectified linear unit. In this function, if the input is positive, it returns the same value. If the input is negative, it returns 0. For positive values, it does not compress the output. So the gradient remains strong, and because of this, learning becomes faster and more stable. That is the reason ReLU is widely used in hidden layers. ReLU and sigmoid both return a single value. Now what if we need multiple outputs? For that, we use a function called softmax. Softmax is mainly used in multi-class classification problems. Instead of giving a single output, it produces multiple outputs. Each output represents the probability of a class. For example, if we are reading a handwritten digit, then we will have 10 outputs. Each output will have a probability value. And all these probabilities will add up to 1. So the model will choose the class with the highest probability. Now let us see how this fits into the whole process. A neuron first calculates the weighted sum. Then the activation function decides how that value should be transformed before passing it forward. Without activation functions, even a deep neural network will behave like a simple linear model. So activation functions are what actually give power to neural networks. Now till this point, we understand how the network produces an output. But we still do not know whether that output is correct or not. So in the next part, we will understand how we measure the error in prediction using loss functions. Now till this point, we understand how a neural network produces an output. We pass inputs, apply weights, add bias, apply activation functions, and finally get some output. But here comes a very important question. How do we know if this output is correct or wrong? Because without knowing that, the model has no idea whether it is doing a good job or a terrible one. And this is exactly where loss functions come into the picture. A loss function is simply a way to measure how wrong the model is. Think of it like a report card for the model. If the prediction is close to the actual value, the loss will be small. If the prediction is far from the actual value, the loss will be large. So the goal of the model is very simple. Reduce the loss as much as possible. Now let us understand this with a simple example. Suppose you are predicting house prices. The actual price of a house is 50 lakhs. Your model predicts 48 lakhs. So there is a difference of 2 lakhs. This difference is the error. Loss function takes this error and converts it into a number that tells us how bad the prediction is. Now, depending on the type of problem, we use different loss functions. Broadly, there are 2 types of problems: regression and classification. Regression means predicting a continuous value, like house price, temperature, salary. Classification means predicting categories, like yes or no, spam or not spam, will the player score a goal or not. Let us first talk about regression. In regression problems, one of the most commonly used loss functions is mean squared error, also called MSE. The idea is very simple. We take the difference between actual value and predicted value. Then we square that difference. And then we take the average over all data points. Now you might ask, why square the error? Because if we do not square it, positive and negative errors can cancel each other. Also, squaring makes larger errors much more noticeable. So if the model makes a big mistake, it gets penalized heavily. Let us take a small example. Actual price is 50 lakhs. Prediction 1 is 48 lakhs. Prediction 2 is 30 lakhs. In the first case, the error is small. In the second case, the error is very large. MSE makes sure that the second mistake gets punished much more than the first one. So the model learns to avoid big mistakes. Now let us move to classification problems. Here we do not predict a number like price. We predict probabilities. For example, in our football example, the model might say there is a 90% chance of scoring a goal. So here we use a different loss function called cross-entropy. Cross-entropy checks how confident the model is about the correct answer. If the actual answer is 1, meaning goal will happen, and the model predicts 0.9, that is good. Loss will be small. But if the model predicts 0.1, that means it is very confident about the wrong answer. Loss will be very high. So cross-entropy does one important thing. It punishes confident wrong predictions very heavily. And it rewards confident correct predictions. That helps the model learn faster and more accurately. Now let us connect everything together. We have input. We pass it through the network. We get a prediction. Then we compare that prediction with the actual value using the loss function. This gives us the loss. Now comes the most important part. How does the model improve? The model uses this loss to adjust its weights. If the loss is high, it means something is wrong. So the model updates its weights in such a way that next time the prediction becomes better. If the loss is low, it means the model is doing well. So only small adjustments are needed. This process of adjusting weights based on loss is what we call training. So in simple terms, prediction tells us what the model thinks. Loss tells us how wrong the model is. And training is the process of reducing that loss again and again. Over time, as the loss keeps decreasing, the model becomes better and better. Now you can see how everything connects. Activation functions helped us produce meaningful outputs. Loss functions help us measure how good or bad those outputs are.